the second main day of PLDI, and I have a just brief announcement. So we thank you for the sponsors, and we have a few special schedules. So yesterday I said that at break time, afternoon break times, there is a social event for students, and we prepared some Korean rice cake. But the hotel said that you are not allowed to eat any food from outside, because if there is some food poisoning, then it's all this hotel's responsibility. So they cannot allow. So we prepared, but yesterday we couldn't, and also we cannot give it to you today. So there's no extra food. I'm sorry, but that's the rule. And so, but you can students can get together here in this room, and then the coffee and cookies out there, so you can have some chatting and some, have fun here. Okay, and then there will be student research competition at the same time with the industry session. So both start at 3:20, and the industry session is here. So if you want to hear from our platinum sponsors, you can please come here. And SRC finals at Lilac. And so we will have a business meeting at 5 in the Orchid Room in the second floor, and where I will talk about, just briefly, the Korean alphabet and computer science. And also at 7 p.m. here, so we will have a banquet and awards, and the banquet is at least 6 course meal, maybe 7, and so please come everybody and enjoy. Okay, thank you.
Good morning, everybody. So I got the privilege, because Zach, I think actually wanted to not do it. No, I'm just joking, but he gave it the privilege to introduce Leo. Leo is someone who needs very little introduction. He has built some of the most impactful tools in formal methods, automated reasoning. Many of you have used them, Z3 and now Lean for much of the last decade. On top of being an extremely talented programmer and really pushing the state of systems in this world, Leo's also been a great mentor and community figure. I remember when I was a second-year grad student, I was working on my own proof assistant, which didn't last very long. And I met Leo, and he just encouraged me to come work with him, and really many other people in the audience who are now working the Lean team, kind of, even though we had very little experience doing this stuff, helped us grow into new researchers and build some really great stuff. And so I think not only does he represent the technical part of the community, but also the social good part as well. And with that, I'll let Leo take it away.
Thank you, Jared. I mean, so happy to be here. Let's see if I can get my computer home again. Hi, everybody. I want to get you excited about Lean. Today is a really special day for me because Jared is here, he contributes to Lean. But also Sunho, that I started Lean with, is here. Sebastian Ulrich, that is a co-founder of the Lean Flow with me. Gabriel, that contributes to Lean for so many years. They're all here. It's a special day. Okay, Lean, the beginning of the project was all about software and hardware verification, right? We all want verified systems, right? We want these systems to behave as we expect, right? We want every proof for correctness we want to be able to check them independently with external checkers. That was the origin of the project. But before Lean, there was Z3. Z3 is a state-of-the-art SMT solver. It has been very successful at Microsoft at bug finding, right? Microsoft Sage by Patrice Godefroy caught so many bugs at Microsoft, right? Patrice has so many good statistics showing the number of critical failures, security vulnerabilities decreased dramatically after Sage. But on the other hand, program verification was always a part that was tough. I mean, we had so many unhappy users in software verification. I remember Nick complaining about Lean. Nick is here today, a great former colleague. He would complain about Z3 many times to us, to Nikolai and me. People using Daphne would also complain. And the problem is undecidable. It's really hard to have a push button tool that will work when the complexity goes over a specific threshold. And Lean started with the goal of addressing this hole we had, right? We want to have a tool that would have the best of interactive and automated tier improving. Lean today is an open source programming language and proof of systems, right? One thing that was unexpected, we never planned in the beginning collaboration was not even in our radar. But many of the math folks that use Lean, they say the main thing is collaboration for them. It enabled them to collaborate with people they never met. This is a recurrent message we receive from our user base. Lean tooling, all the tooling in Lean is implemented in Lean, right? Lean is very extensible. If there's one thing I want you to take away from this talk, is Lean is extensible and you can make it your own, right? The math community did it, and we have many other examples of people that made Lean their own. They built their own system inside of Lean. And Sebastian and I, we are really proud of our tooling is all implemented in Lean. The LSP server, the parser, the macro system, the elaborator, the type checker, and so on, they're all implemented in Lean. And Lean has a small trusted code base. At the beginning, it felt like all proof of systems, all major proof of systems, Isabel, Rock, Agda, well, not Agda doesn't have a small trusted core, but many proof of systems have a small trusted core. At the beginning, Fuzzy said, oh, we have to do it too. And we had many soundness bugs in the passing in Z3. It felt like a good idea to have a small trusted core from the beginning. But we didn't see, one thing that we didn't expect, that many people that are excited about AI today, they care a lot about the small trusted core, right? They know the AI can exploit and will exploit any soundness bug in your tool, right? They are trying to increase, they have a goal, they want to achieve the goal. If using unsoundness is the best way, they will do it, right? And now, for many, I mean, Lean started 12 years ago, but 2 years ago, Sebastian Ulrich and I launched the Lean Flow. That's a non-profit dedicated to the development of Lean. From the beginning, right, Lean was based on dependence type theory. Right. We were studying many of the different approaches, and one thing, we wanted a system that would be great for math. Our first user was Jeremy Avigad. He's a mathematician, and he made this point over and over again that in abstract math, you need to manipulate many objects like groups, rings, fields, and they all should be first-class citizens. You should manipulate them as objects in your language, right? And there's no other way around. Of course, some people would say, oh yes, you can use this crazy encoding, but we do not want our users to be distracted with encoding tricks. So people that claim that you can use a fancy encoding is the same people that would say, oh, you can program anything in a Turing machine. Who is going to do that? Nobody. Right? You want to work at the right level of abstraction. We wanted to enable our users to focus on the math, not on encoding tricks. Here's an example from Kim Morrison. Kim has been contributing to Lean for 10 years. He works with us at the Lean Flow. And here, Kim defined an example that's going to be in our manual. Index map is a mapping from alpha to beta that you remember the order things have been added, inserted into the map. The map here, the first thing you see, the first feature in the first line, Lean has type classes. The alpha should have a Boolean equality, is this BEQ, and should also have a hash function. That's what it means to be hashable, right? Then you have 3 fields that are data, indices, keys, and values, right? And the 2 last fields are propositions you can view as invariants that any element of this structure should satisfy, right? The first one is that the array's keys and values have the same size. And that's why we call it dependence type theory. the type of these fields depends on the previous fields. That's why it's called dependence. And Lean here, you can also, when you define a field, you can tell Lean the default way to synthesize values of these fields. If it's not provided, what you should do. In this case, you should call a proof of automation called grinds, right? And the same thing for the well formulas fields. It's basically saying that for every integer, every natural number I, right? If there is a value at position I in the keys array, then this value, the indices map this value A back to I, right? They are saying one is the inverse of the other, right? And again, if this field is not provided manually, a proof will be synthesized. Lean will try to synthesize the proof automatically using grinds, right? It can be any tactic, right? Any piece of proof automation you want. In this case, you're saying it's going to be grinds, right? The full example is here. The slides are available online. You have the link at the ends, but you can see the whole example here. And then Kim defines the insertion function, right? The insertion requires an extra property, that's the alpha. The Boolean equality is not just a function, a binary function to a Boolean, but is also lawful. What it means is it returns true. The elements are indeed equal to each other, right? So you cannot return false everywhere, for example. And then it proceeds as follows. You check the hash map indices. If the element is there is a value I there. You just update, otherwise you insert the new elements, right? And you see the two fields have not been provided at all. The proofs have been synthesized. The code looks like a regular code that you would write in a language like OCaml, but the proofs, the invariance, Lean is proving behind the scenes. If you want, you can prove yourself manually, provide the proof term. If the automation does not work, you can provide the proof yourself. But by default, Lean will try to synthesize the proofs automatically for you. And as an example, Kim tried to make the point here that there is a difference between library building time and library usage time. Right? Some annotations it provides for the proof automation are local, are used just during library developments when they were developing this module. Right? After they are done, you can expose to the users the theorems they want to use when using this mapping in their own programs. Right? So here you have 4 main theorems that you are going to use. And all proofs were done automatically using grinds. Theorems in Lean are like definitions. As any other dependently typed theory, there's no real distinction between proofs are terms, right? Types, propositions are types, right? The same thing is true in Lean. The only difference in Lean is that when you say something's a theorem, the system will enforce the resulting type to be a proposition, right? Otherwise, you will reject. Okay, another thing, people ask us over and over again, what's the secret, why Lean is successful? For us, one thing that we really do is listen to our users. Lean has good support for classical mathematics from day one. Right? Our first user was a mathematician, was Jeremy Avigad. The math community using Lean is growing rapidly. They love the system. I remember Clark Garrett told me a few weeks ago, he's a professor at Stanford, saying, wow, one thing that blows my mind is that every single Lean user I meet, they love the system, right? And making sure for math, the math folks, constructive mathematics is a completely alien thing. None of them don't even, advanced math, you cannot even write. You would have to rebuild so many things from the ground up to be able to do the math they're doing using constructive principles. They do not care about that. They want to operate the way they operate. All fields medalists today use classical mathematics, right? And Lean has great support for that. Also, another thing, it's funny that people like Kevin Buzzard, Terence Dow, they come to me saying, oh, you computer scientists, only you are constructivists. This is not true. Most computer scientists couldn't care less, right? Developers don't even know, most developers don't even know what constructivism is. And verification engineers, they only want to get the job done, right? They want to finish the proof, right? They don't care if the proof is constructive, is classical, they want to get the job done. MathLib. MathLib is the Lean mathematical library, right? It's a project with over 500 contributors. It's reaching 2 million lines of code. It has more than 100,000 theorems inside. In 2020, we had this article in the Quanta magazine. There are many really nice codes. My favorites from Heather Macbeth, when she says she's investing time because in the future she wants people to have an amazing experience. And yeah, she predicts the future. Many people benefit from MathLib. We like to say that Lean is a development environment for formal verification, right? It has a rich user interface and integrated tooling, right? The tooling, we have a build system that's called Lake. It's Lean Make, it's a funny joke. And he's our Cargo, right? It's inspired by Cargo. And okay, since it's called Lake, the build system, okay, Rust called their package crates.io, ours is a reservoir, right? And the environment provides runtime feedback, real-time feedback, errors, goals, hints, and so on. And it's funny that Jared did the introduction today because he insisted from the beginning, he actually was really annoying in the beginning saying, we need to have great tooling, we need to have great tooling is essential. He was right, but it was annoying. At the time, we would have bare bones things. And Jared kept insisting we needed great tooling. It took many years to get great tooling. But he was right. It's super important for our users to have great tooling. And here is the Visual Studio codes interface. That's the favorite used by the Lean users. Vim is the second. I mean, there are many math folks that use Vim. The interface with Lean is also really great in Vim. But in VS Code is getting better and better, right? Mark Huizinga, he works full time to provide a great experience to our users. You can click anywhere in a Lean proof on the right hand side. Can be even a different monitor. I mean, Mark spent time making sure this works smoothly. You have the info view. And this is not a static object, it's interactive. You can hover and get extra information about anything there, right? For example, I don't know what M prime is. Oh, M prime is a submodule of M. Oh, I don't know what a submodule is. Lean will keep jumping to the definition, right? And you can keep going. I mean, I don't know, a submodule uses an additive submonoid. I don't know what it is. You can keep jumping. That's one thing that Kevin Buzzard would say. With Lean, if you want, you can keep zooming in until you go back to the axioms of mathematics. And when he starts using Lean, that's one thing that got him really excited. He would say, math is data now, you can transform it, right? And the same infrastructure that we have in VS Code is also used for a documentation outreach system called Verso. It was built by David Christiansen, and Verso, all the documentation is interactive, right? And uses the same infrastructure. We call it, since everything is integrated in Lean, we claim that we have flywheel improvements to any of the pieces help each other and provide a better experience to our users. Let's focus a little bit on mathematics now. I mean, that's how Lean became popular. Today, it's mind-blowing to us. I mean, sometimes Sebastian and I feel like we don't believe it's true. But we were joking a few weeks ago that we managed to get the greatest living mathematician recording YouTube videos online showing him using Lean, right? And he keeps using Lean with different AIs. And for him, the main big deal in Lean is large-scale collaboration. He told me when first time I met him, I never imagined that one day in my life I would get a contribution from an amateur mathematician, right? I only work with the best, but now I get contributions from people that are not even mathematicians, even computer scientists contribute sometimes. And for him, this was mind-blowing. He doesn't have to check the contributions because he's checking with Lean. And he also envisions this kind of system as the future for math, because now he envisions a future where people are going to be interacting with AI. There will be humans and AI working together to solve really hard problems. And just by coincidence, this Saturday, they release a podcast with Lex Fridman. If you don't know, Lex Fridman is one of the most influential podcasters in the US. And he had a 3 hour and 40 minutes and 15 seconds to be the pie interview with Terry. And Terry spent more than 40 minutes talking about Lean. I mean, we're really happy. There are many other major projects today. Fermat's Theorem by Kevin Buzzard, that is massive. Nobody today understands. I think Kevin even claims that nobody ever fully understood the Fermat's Theorem proof. People understand parts of it, not the whole thing. Having it formalized will make sure these results will survive, because Kevin believes people are dying. The few people that understand the pieces will die, and nobody will know the proof anymore, why it works. But how did we get here, right? Kevin had an instrumental role in our journey, right? In 2019, he said, we have to do modern mathematics, cutting edge math. Nobody cares about a result from the 70s. We have to formalize modern mathematics. And he decided to formalize perfectoid spaces. This is a mathematical object defined by Peter Schulze. Was not by accident. Peter Schulze got a Fields Medal in 2018, and Kevin said, okay, let's do it. I mean, let's see if Lean is powerful enough to formalize this object that is extremely complicated. They did not only succeeded, but they learned important lessons. One of them is that math is data. You can produce a dependency graph automatically. Now that math data, you can refactor proofs using tooling. You can write tooling that analyze your data. All of that was news for the math folks. With the success of Perfectoid Spaces project, Peter Schulze himself, he challenged the community in 2020. He said he had a new result. He was obsessed about it in 2019. He was not sure about if it was correct or not. He felt like everything was correct, but nobody would dare. The complexity was so high that nobody would dare to check all the details, right? And I remember Kevin in December came to me saying, it's going to take years. We're going to do anything. Kevin is like that. We're going to do anyway. Even if it takes years, we are going to do it, right? But to our surprise, a team led by Johan Komelin did it. The main result, the main crucial lemma that shows he was unsure about, they verified in a few months, right? He made the announcements, the main results. It was a big deal. I mean, they fixed many mistakes in the proof, all small ones, I mean, local things that can be easily fixed. And these results showed up in Nature. It's a big deal. Math results usually do not show up in Nature, right? But didn't stop there. I mean, for me, what was the most unbelievable thing they achieved is that they did not only verify the whole thing, but they simplified the proof without understanding the proof. Johan would tell me that he could see only 2 steps ahead. They replaced an object called the Brindleline complex. Don't ask me what it is, I don't know. But they replaced, for me, it's a data structure. They replaced this data structure called the Brindleline complex with a much simpler one. And the proof still goes through with the simpler one. They did a refactoring step in our terminology, using our terminology. And Johan was saying, Lean was a guide, right? He managed to do all these simplifications because there was an assistant next to him, helping him along the way. Then I read this, Peter wrote a blog post. I mean, it's unbelievable. I mean, he's a Fields medalist, but he wrote a blog post. There was a quote there. I said, come on, he did not write that. I mean, I started checking with Kevin. No, this was what Peter wrote, that Lean was really an assistant, navigating, helping him to navigate through this thick jungle the proof is, right? Basically, he was saying the object, he couldn't keep all the details in his head, right? This is one example that I was happy. Another example I was really happy is from Kim Morrison. Kim joined us in 2015, around 2015, the very beginning. I remember the beginning, I thought Kim was insane. I said, what this mathematician cares about Lean? The system is barely usable at this point. I thought they were nuts. I mean, but kept building. Kim is one of the founders of MathLib. And I remember at the time he said, oh, I'm working in quantum with one of your colleagues, Mike Friedman. Mike Friedman was leading the quantum team at Microsoft. He's also a Fields medalist. And one day he came to my office saying, Kim is the smartest person he knows. Yes, Kim is really smart. But recently, Kim formalized his paper, the results from his paper in Lean. And they told me that there was a bad taste in their mouth because when they published the paper, the results were checked with a computer algebra system. And for mathematicians, it's like blasphemy to have something that's an unverified computer algebra system checked. Feels like your result is not real because you needed this computer algebra system that people believe there are many bugs. But finally, we could check again the results. And here, one of the highlights is that we are reasoning at abstract math. You're saying there's any commutative ring that have characteristic 0. This is not a toy. I mean, this example encodes real algebraic constraints derived from relationships among diagrams in a pivotal tensor category, and it can be checked in milliseconds in Lean. And Kim was excited because this was demonstrating now that we can finally explore mathematical and physical structures, like from topological quantum field theories to fusion categories, right? And the tooling is now finally good enough that you do not have to rely on computations done by hands or unverified computer algebra systems. And Kim, besides being a great mathematician, also assisting us building Lean itself. For example, this grind tactic, Kim is a key contributor to it. And also to making sure that our users are happy. A few weeks ago, for example, Terence Stahl wanted to reason about linear ordered vector spaces. You can use a variance of linear arithmetic, but it's not, you have to change. For example, you cannot use SMT solver here. SMT solver is a hard-coded for integers, natural numbers, reals. Here you have something that's not a natural number or an integer, right? It's an ordered vector space. It's also not a commutative ring. That is usually the structure that most proof assistants build linear arithmetic on top of. It's a variance, and we made it to work to make sure our users are happy, right? This is super important to make sure that we remove the roadblocks that allow them to scale, right? Software. Let's use the second half. I want to use the second half to talk about software verification. Today, after this huge detour through math, Lean is used in many software verification projects, right? You can write code in Lean and reason about it simultaneously, right? You can prove your code as the properties you want. CIDR was the first project to use Lean at AWS. CIDR is a policy language, right? They wrote a model of CIDR in Lean. a model is executable, and they proved key properties about this model, right? The setup is as follows, right? Cedar that runs in production is implemented in Rust, right? But they have a model written in Lean, and they prove many different properties about this model, and they use differential testing to show that the model and the code in production behave the same way. If there is a discrepancy, something will have to be fixed. And Minator led this project. For her, a big deal was the fact that Lean is fast. The model you can execute more. Actually, in her experiments, her modeling Lean is faster than the production code in Rust, right? Enables them to verify many tests overnight. Another thing for her that was a big deal was maintenance. Maintaining the proofs before using Lean was a nightmare to keep the proofs maintained. They would break all the time when people would update the verification technology. Should spend weeks patching proofs. Now, minutes. She fixes everything when a new Lean version is released, right? If you want to learn more about Lean, you can check her blog posts. Kasia and Mina wrote a blog post in 2024, last year. You can read more about how Lean is used in their projects. SAMCert, I will not tell you much. We had a talk yesterday about SAMCert. It's an open source library for verified differential privacy. One thing I really like about this project is not the fact they verified, but they made it twice as fast. Because now you could verify, you can implement aggressive optimizations without fearing the introduction of bugs, right? And I love this quote from Jean-Baptiste. Many of you know Jean-Baptiste contributed to CompCert, was a key figure in the CompCert project. And one of the quotes I love from him is that SAMCert would not exist without MathLib, right? He told me he felt like a kid on a candy store. All the pieces he needed were there. He needed for analysis, number theory, topology, every single bit was there. He did that in record time. I mean, people that know Jean-Baptiste know that he's really smart, but I was blown away how quickly they managed to push this project forward. Since then, he learned to love the fact that Lean is a efficient programming language. And he pushed new projects like TensorFlow using Lean. Verified cryptography at Microsoft. This one is funny. When I met them, they said, "You silly, you just had to leave for us to start using Lean." I mean, now that you left, we are using Lean for verifying crypto. They had a blog post recently about Syncrypt, where they are modernizing their crypto libraries and porting them to Rust and verifying using a tool called Aeneas. Sonho developed Aeneas. He's now at Microsoft too. You're working with Jonathan Prochenko. And for them, one key differentiator was that the fact that Lean was extensible. They wrote their own proof automation, right? And also they relied on MathLib, right? For them, MathLib was a key asset. I remember Cedric is part of the team. I know Cedric for more than 20 years. Cedric's not the kind of person that compliments people, but he spends, last time I had dinner with him, several minutes praising MathLib. And I said, "Can I record you saying, could you say it again?" And I record, because it was so nice. He's saying, "MathLib gives me the results I need at the right level of abstraction," right? And their setup is a variant, is a variant of what Cedar uses. Here they have the Rust code, but they use Aeneas to automatically translate the Rust code into Lean, and they verify the model that was automatically generated by Aeneas. The software engineers only touch Rust, and the proof engineers only touch Lean. Someone was telling me that he was using Aeneas and developing Aeneas and writing many extensions. I took a look, let's see what he's doing with Lean. I was blown away. He has lots and lots of extensions. I got a few examples just to highlight some of the features. For example, he defines his own tactic syntax. You see it's very elaborate. You have optional elements. The to is optional. You have an optional list of terms, and you have a location that's optional. And then he writes a function that's the handler, that's in our tactic M monads that we use to write tactics in Lean. And you have pattern matching that Sebastian implemented, this pattern matching for syntax. It's not just, it works even for your own syntax. You can define new categories in Lean. We have expressions, you have commands, but you can define your own syntactic categories, and the pattern matcher will work. It's a great productivity tool. It's great to see it being used in this example. Another thing is not just that you're adding new tactics. You can add extensions to the Lean simplifier. As any proof assistant, the term simplifier is a major working horse. And here, Sonho implemented his own simplifier extension and his own hook. I mean, in Lean, you can attach whenever you see some pattern, you can put a trigger to call some code that will simplify the term. Of course, you produce a new term, not just a new term, you have to generate a proof that it's equal to the inputs, right? And also another thing, evidence, a piece of evidence that we really care about our users. Sonho came to us, his proofs are gigantic, right? And at the time, Lean would have only parallelism. It would basically go at the file level, you could compile many files in parallel, and when you change a proof, you should go to the beginning of the proof and process from there. For the math folks, this was good enough, but for Sonho was not. And Sebastian implemented many cool things, but this one is really cool, that you compile the whole Lean file in parallel now. I have here an artificial example. I love to see this orange bar showing which all the parts that have been compiled in parallel by Lean. And it's really fun when you are working, you see things moving, being proved completely automatically, all in parallel. And Sonho was really pleased that Sebastian implemented this feature for him. That's one message. I mean, Lean is extensible, and you really care about your users to get them using your system, right? This week, we had this nice surprise from Ilya and Vladimir demoed Veil to us. We were blown away. I mean, I remember when we were beginning Lean 4, Lean started in 2013, but we wrote it a few times. Lean 4 is the last one. The lesson is going to be the last. We're not going to start from scratch again. But when we started Lean 4, with all the lessons we learned, one thing Sebastian and I kept saying, we want people to define domain-specific languages inside of Lean. Right? You want them to be able to do that and leverage all the tooling, the proofs, the proof automation we provide, the syntax. This is a Lean file. I even asked Ilya, this is a Lean file? I couldn't even recognize. He defined his own DSL, right? And everything, right, is being checked by Lean. He has bounded model checkers, he's calling SMT solvers. If the automation, the push button automation does not work, you can go back to interactive proving, right? I put a link to the website. You can also check their latest paper at CAV. They also have a separation logic framework for Lean. Is also in their GitHub repository. But if you care about protocol verification, a series of blog posts by Igor Konov is also, they are great. I mean, he's just learning Lean. We were really impressed. I mean, we learned from Mark Brooker. Mark Brooker is a vice president at Amazon. He really cares about protocol verification. And he sent me the first blog post saying, look, take a look at that. Igor, he defined a protocol that is two-phase commits in Lean, and he wrote a simulator. In Lean also. He wrote the protocol in Lean, wrote a simulator for the protocol. It's a generic simulator for like doing some kind of model checking in the protocol. And he was blown away that his simulator is faster than the model checker he was using before, right? It's not just faster, it's like a little bit faster. It's like, I think it's 168 times faster, right? And after that, he proved the protocol corrects in Lean. Of course, he's a new user. He doesn't know all the proof automation that's available, but it was quite impressive. He also proved its liveness properties. And I love this quote from him saying that no other interactive tier improver captured my attention for so long. I mean, he made our day. KLR. KLR is another project at Amazon. It's part of the reference implementation for our neuron compiler for generating GPU codes. It's a project led by Daniel Cronin. He's here. You can learn more about it. But again, here, another highlight is that Sean is one of the main people pushing the project, developing. He put this code, he didn't send to me, it was in an open Slack channel at Amazon. He was blown away by the metaprogramming. He was saying metaprogramming is amazing. He managed to remove a lot of boilerplate codes. And these compilers have tons of boilerplates, and he could automate everything using Lean metaprogramming. I recall before joining Amazon, I was talking to Sebastian. We like to view us as we design Formula One cars, but we need to find pilots. And Amazon has so many good pilots, like Emina, Jean-Baptiste, Sean is another one. They are amazing. And it's open source. You can check their codes online. And they use bit vector reasoning, right? Here, like this decoder here. And it's a good, I select this part because it's a good segue to another piece of automation we have in Lean that we are really proud of. Is BV Decide. BV Decide started, it was an epic battle to get everything. It started in 2023 with Josh Kloon. Josh Kloon was my intern at Amazon, and his project was to write a verified LRAT proof checker. LRAT is a format for produced by SAT solvers, right? It's optimized for SAT. Right? It's way more efficient in coding than you'd get if you were using proof terms that are available in Lean. And he wrote a checker in Lean. He verified this checker. The checker leverages many performance improvements we have in Lean, like many of you at PLDI are familiar Perseus. I mean, Dan Lyon had this paper a few years ago where he describes Perseus that use a technique similar to the one we have in Lean, in Coca. And this is the performance we get there is key. Perseus was key to deliver the performance we have in this proof checker. Again, is the flywheel. Right? The fact that we have efficient code generator was key here. After that, Henrik Boving, he implemented a verified bit blaster in Lean and a verified CNF translator. It's not just for bit vectors, also for finite types like scalar types, structures that only contains finite types. His BV Decide tactic can handle all that. And we use a very efficient set solver, CAD-Cal from Armin Biere, right? And this tactic is great. I mean, it's like a number crunching, right, thing. For example, let's see how we use it to verify pop counts. Pop counts is from this book, Hacker's Delight. It's this really obfuscated piece of code that you can compute the number of 2 bits in a bit vector, right, without using any loops, right? It's really mysterious piece of code. But then you have, on the right-hand side, you have pop spec, is the specification where we use a recursive function in Lean to count the number of bits. Another thing to highlight here is that on the left-hand side, you see we have imp is a GSL we created for this example. It's a GSL for this imperative language. It's embedded in Lean, you can write it, you can get syntax highlights, everything. And now you want to prove that the two coincide with each other, right? We wrote the theorem, and basically you use simp, the Lean simplifier. Simp here is exposing all abstractions, right? Reducing the problem to the language of bit vectors. After you have a problem that's only bit vectors, you call BV_decide and your proof is done. Here, the automation you see is surgical. We use simp to expose the abstractions. There's no guessing, you are telling exactly what we want to expose, and you get a bit vector problem, and you call BV_decide and you are done. Another question we get all the time is, does Lean have hammers, right? Hammers are popular in proof assistance, right? Yes, the community is building that, actually true now, being actively developed. Lean Hammer at CMU is calling first order, not even first order, it supports a little bit of higher order logic, superposition. They do proof reconstruction in Lean. Lean Hammer is already available. And there's also Lean SMT from Stanford that invokes CBC5 and will also do proof reconstruction, right? And Clark has many students working on this project. Yeah, it's again, all of them are using extensibility. They're using the Lean metaprogramming, right, for doing the proof reconstruction. We saw BV_decide as a tactic that reasons at the bit level for bit vectors. We saw that grind allows you to reason at higher levels of abstraction. For some bit vector problems, you can solve them using the fact that a bit vector is a commutative ring and has characteristic, in this case, since it's 16, 2 to the 16, right? And this equality holds always because 256 times 256 is 0 for a bit vector, right, of size 16. That's why this equality holds, and grind knows that, right? Here it's exploiting the fact bit vectors are commutative ring. There's no bit blasting going on. And grind also allows you to write programs in a very clean way, like the sift down from heap sorts. All these array accesses in Lean, you have to provide a proof that the indices are in bounds, right? And here this is all happening behind the scenes. And grind is not just arithmetic. It knows, for example, that swap. It knows that when you swap two elements of an array, the size is preserved. And this is key to finish. To not, if you grind did not know that, you would have to write these proofs manually. They would catch in your way, right? And to prove that sift down preserves the size of the array is also just a single line. You say use functional induction and then apply grind to each subgoal. Functional induction is just an induction that abstracts the control flow of your procedure. Diagnostics. We like to say that proof automation is great when it works, but it's even more important for it to explain why something did not work, right? And in grind you have very detailed diagnostics information. For example, it will produce an assignment for the linear integer constraints. You can also see, you have many folders and you can open, oh, which propositions grind knows to be false. It will tell you. It will also tell you matching instances. We heard a lot about matching during this PLDI. Matching is a technique for instantiating theorems, right? And sometimes you want to know, a recurrent problem is that you instantiate too many theorems and you're consuming a lot of memory. You want to know how many times each theorem was instantiated. you know, Grind tells you exactly. You can diagnose what's going off something that's off or is consuming too much memory. You will find out. And again, the flywheel again. This is using the same infrastructure we have for providing type information for terms is also here. Oh, you don't know, you don't remember what array gets lm set ne is? You hover, it will show you the type. You know exactly what is the type of this theorem. Okay, but what exactly is Grind? Grind is inspired by SMT technology. You should view it as a virtual whiteboard where you are learning new facts and putting on the whiteboard the procedure. And there are many engines that cooperate to put more information on the whiteboard. And it works like every single SMT solver these days. You keep merging equivalence classes. And the engines are congruence closure, matching, constraint propagation, guided case analysis, and many solvers like linear integer, solvers for commutative rings, for linear arithmetic, but for abstract structures. It's unlike, differently from SMT solvers, it supports dependence type theory, right? You do not need to do any encoding trick. It works directly on your goal. It understands the type class mechanism. It understands dependent pattern matching. It can pattern match, do case analysis on match expressions, and it produces lean proofs, right? What it is not, right? I think for us it's really important to set the expectations for our users. It's not a tool for doing massive case analysis, right? For this kind of search, you should use BVD size. If you're doing massive case analysis, your proof term is going to be gigantic, right? Especially if you represented it as a lean proof term, would be a huge waste. It's much for this kind of problem when you're doing massive case analysis. It's great to have a custom certificate for that, like we have in BVD size, using the LRAT formats. One key takeaway here is that if we view like, because you provide diagnostics in grinds, for us, if you see that your grind is going to performing a lot of case analysis, many case splits, the idea is that you are using it wrong, right? That's not how you should use it, and you should switch to a different tool. A few years ago, sometimes I think Kim is very competitive, but a few years ago, Ruslan Leno, Shankar, and Stefan Merth, they challenged the link. They created this challenge: if then else normalization procedure, like something that would normalize all if then else's in your in this data structure. Make sure they had many things. They provide a list of things that should be normalized. Ruslan approached me. I want to see you to solve this challenge. I didn't even try. I just posted on Zulip. In Lean, Zulip is the channel where the community gathers. We have really smart folks there on Zulip, really smart folks. They solve it in record time. I mean, people are blown away. These folks are really smart, but their solution was a really big manual proof, right? And Kim was not happy, said, okay, I'm going to do it again, but using grinds. And did it. Of course, I'm putting just the main function here, but all proofs are single liners, right? Again, the main results is he proves that the code respects the spec is one line, function induction followed by grinds, right? But you may say, oh, how do I find out that I have to use function induction? Actually, we have a tactic called try. Kim likes to tell users, you have to learn one to become choose Lean. Learn to use try question mark. You put try question mark, and Lean will tell you what works. You will try many different things. Hopefully, Sebastian one day will make it do in parallel. He told me he would do it, and you do it to run in parallel, and you show all possible things that work for solving the problem, right? And The cool thing, again, I think it's not a surprise that it is extensible. AI. Let's talk briefly about AI. Lean enables verified AI, right? This is really important because large language models, I think by now everybody agrees they are really powerful tools, but they hallucinate, and a small mistake in a math proof, right, invalidates the whole thing. And it's amazing, especially if you want a result that there is a bogus proof in some textbooks. It's impossible to convince the LLM to give you the right one. It's like it's burned in their memory that's the bogus proof, and they keep giving you the wrong proof over and over again. I mean, it's really annoying. But with proof assistants, we believe they are the antidote for hallucination. Proof assistants can also help AI, right? You can use proof assistants to generate syntactic data that's correct by construction. Later today, Sunho he's leading a project called AI Lean at Amazon, and he will talk about how he's using Lean to generate syntactic data. He has really great results. He's using Pentagraph by Lenny Aniva from Stanford. Pentagraph is a tool for extracting data from Lean repositories like Mathlib. Pentagraph is getting really popular. I know a few startups that are using Pentagraph now. But AI can also help proof assistants, right? You have many groups building AI for Lean, from Caltech, OpenAI, Meta AI, Google DeepMind. Claude 4 is fantastic on Lean code. It's really good at explaining, creating proofs. Even the system cards that the manual they release comes, the latest one has a Lean example inside. But it's impossible to talk about AI without talking about Alpha Proof, right? Alpha Proof is this AI that Google DeepMind built on top of Lean that got a silver medal at the International Mathematical Olympiad. The IMO is really hard, right? Many of my colleagues did not thought this was possible. It's crazy, but even Turnstile, I think he did not think. I mean, we are in a committee of an open source competition, and I think he was preparing his talk for the first edition of this open source competition for the IMO. He was preparing his talk. He did not expect that Google DeepMind would release these results a few days before his talk, right? And now they also have this new initiative called Formal Conjectures, where they're collecting many open conjectures in mathematics in Lean, right, and make them available on their GitHub repository. Auto-formalization is also a key area, lots of activity there. It's the process of converting natural language to formal language automatically. And last week I was joking with Sebastian that was really eventful week. On top of all these things, Turnstile, there was these results. I was casually listening. I couldn't attend the Big Proof seminar, and Bavik was giving a talk. I was watching online the talk. Bavik had many contributions to Lean, Mathlib. He verified results that before they were published. I mean, he's a student from Chingowers, that's a Fields medalist. He was part of the Alpha Proof team. Last week, he was giving a talk about a new result he was formalizing that relies on a result by De Bruyne, a result from the 60s. And this result was auto-formalized automatically by a new system that Christian Zagadi is building at Morph Labs. Their system formalizes the paper, right, in Lean, and Bavik just used the results. I was blown away. I think nobody was expecting that this was going to be announced during Big Proof. Before we wrap up, I like to tell a little bit about the Lean Flow, right? Sebastian and I launched the Lean Flow in August 2023. It now has 19 members. The mission is to improve the scalability, usability, documentation, and proof automation in Lean. We also want to be self-sustainable. In August 2028, it should be like the Rust Foundation. Right now, we rely on philanthropic donations, and we are really grateful. I think it would be impossible for us to run the Lean project without the donations and the whole team now. By numbers, I think our productivity increases a lot. Now we have one release almost every month we release a new version. More than 4,000 pull requests have been merged since the beginning of the flow. We have public roadmaps. Lean appears in many venues since the flow started, 3 times at the New York Times, Quanta, Scientific American, and so on. The release 422 will celebrate the 2nd anniversary of the flow, and we are packing many cool things, like the new compiler, the module system that Sebastian is working on, and many other features. I want to finish also telling you a little bit about CSLib. CSLib is a new initiative. The goal is to be the math lib for computer science. The steering committee, Swaratz and Clark, I think they're the main driving forces. Swaratz is Google DeepMind and UT Austin. Clark is at Stanford and Amazon. And Jason Rose and myself are also helping, right? And the goal, the mission is to have a foundation for teaching, research, and verification efforts, including AI-assisted ones. How can you contribute? You can contribute in many different ways. You can contribute to MathLib, right? You can join the Zulip channel where the community gathers. If you care about machine learning kernels, you can contribute to KLR, right? You can talk to Daniel. Daniel is here. If you want to contribute to a large formalization project, contribute to Fermat's theorem. I mean, there are people all over the place. Kevin tells me that sometimes he creates issues for each lemma that has to be proved. He comes back and people proved everything for him. I mean, if you create your own project, we'll show up in Reservoir. We have more than 4,000 there. You can try Lean live on your web browser without installing anything. And you can also support the flow with funding, partnerships, and advocating the project. Advocacy is super important for us. Well, I hope, yeah, I try to repeat over and over again. I will say it one last time. Lean is extensible. You can build your own system inside of Lean. You can leverage every single piece, like the folks working on Veil did, like Ilya and Vladimir did, right? You are going to leverage the proof automation we are building, not just us, but also our collaborators in Stanford, CMU, and so on, right? You're going to leverage all the IDE, the tooling, the build system, everything, the documentation, right? All the books the community are writing, right? Explaining how to use the system. This is just the beginning. The progress now is accelerating. We truly believe the math community is changing, the MathLib community is changing how math is done. And it's not just about proving, but going beyond your cognitive abilities. Thank you very much. You can get the slides on the QR codes. Thank you.
We have time for a couple questions as well. Okay, Adam's already there. Make sure to introduce yourself as well, everybody, and let's start.
Hey, Adam Japala from MIT. So, as I understand it, despite the examples of like program verification uses you highlighted, the vast majority of uses of Lean are still in math, which has this funny property that though we know math underlies engineering, what mathematicians do in some sense is sort of more similar to professional athletics or something, in that it's kind of part of the point of the exercise that everything you do is really hard, otherwise you're not going to spend time on it. And if you're looking at program verification instead, you're dealing more with lots of really small, individually boring details that you have to thread together in the right way. And this difference can potentially have interesting consequences for the design of formal methods tools. I think in the verification examples you showed, they were all relatively short but interesting programs. And I wonder what you think about what might be different in the evolution of Lean to support something like verifying thousands of lines of code written in some language that's not the native functional programming language of Lean.
Yeah, this is a great question. We really care about that. We have two initiatives for our year 3 roadmap. We have two initiatives to push forward in this direction. One is the WebAssembly. I mean, Joachim Breitner, I saw it. He works for the Pro now, Joachim. And Joachim wants to do WebAssembly in Lean, to do all the verification. This is one initiative. The other one, Cameron Zorek, he's the guy that implemented Rosetta 2 for Apple. He works for the Pro now. And he also works on Apple hardware. He wants to do a front end for Verilog, for Lean, and to push as hard as possible. He believes that we can, he's a no bullshit guy. He wants to make sure, he believes the best way to make Lean self-sustainable is hardware, because he knows the people at Apple that do hardware verification. He said, these people care about correctness, because if they have a bug, screws up everything, I want to make sure that we can scale Lean to really, to real hardware designs. That's two directions we are pushing. And of course, at Amazon, we are pushing a lot in software verification. That's another source. I fully agree with you. I mean, your message exchange is saying, I have doubts about scalability. We have too, but we are going to work super hard to make sure that we'll succeed there too. But you're right. I mean, there are different kinds of problems. One, the complexity, is different kinds of complexity. One is just sheer size, and the other one is really mathematical. I think I liked your term athletics, right?
Thank you.
Yeah, welcome.
Hi, Robert Rand, University of Chicago. Early in your talk, you mentioned that you need to have this small trusted code base, because if you're going to give it to an LLM, for instance, it will exploit whatever it can exploit to prove the thing that you're trying to prove. But as I understand it, Lean can run arbitrary code. It's not like the rock proof assistant where, you know, in order to actually execute something, I need to export it into OCaml and then run whatever comes out of that. So is there a way to make, you know, Lean such that I can trust just giving it to an LLM and let that LLM run stuff on it?
Well, you can trust the proofs, right? The proofs that are built, you can be independently checked. Of course, in Lean, you can write programs that you cannot verify properties. We have a keyword that allows you to write unsafe code. That's critical for writing the parts of the proof assistant that you want to make them super fast. And we use unsafe features. And whenever you use unsafe feature, the primitive is like an opaque primitive. You cannot reason about it. It's like this trade-off. Whenever you use unsafe feature today in Lean, we cannot reason about it. Of course, many people in the Lean community have dreams that one day we are going to have a low-level IR with the semantics, and you can write unsafe features in this IR, and you're going to be able to reason. But today, yeah, we cannot, right?
So is there a version of Lean where I can just exclude all the unsafe behavior and just, you know, to provide that as an input to the LLM so it can?
Oh yeah, no, keep in mind, when you can provide unsafe features, you're not going to be able to prove anything about them. But you can. I mean, in Lean, you can trace back. If you're using a unsafe feature, if you're using an axiom, keep in mind that that's lesson that Kevin Buzzard had is true for us, for code too. Now code is data in Lean. You have APIs to traverse. You can check if you're using a funky axiom. You can write a program that will check if you're using a specific axiom, if you're using a unsafe feature, which functions are used as unsafe feature. you can write a program in Lean that will give you all this information, right? The same way Kevin says, math is data, Lean code is data too that can be manipulated in Lean.
All right, thanks.
Yeah.
All right, I think that's it. Thank you so much again. Let's thank Leo for the great talk.
Hi everyone. Please have a seat so they can start. So welcome to the verification session. So we will start with Sasha, who will tell us about verifying Rust.
Hello. I have to admit, after Leo's keynote and before such an impressive session, I have a lot of pressure, but I'll do my best. Hi, so I'm Sasha. I work at Imperial College. I'm very excited to be here to present that work that's been going on for a long time. This is work in collaboration with Xavier Denis, Petar Maximovic, and Philippa Gardner. In here, I present a new or somewhat new approach to verifying Rust, which we call hybrid. And I'm going to give you context first, which is that we're in an era where people are changing the way they write code. Normal developers, not PL people, are changing the way they write code. They used to write, C or whatever, or Python, and now they write type-check Python or type-check JavaScript or Rust, which is somewhat better than type-check C. And how long have we been waiting for this to happen? We've been waiting quite a long time. And even better than that, what we can say is that these languages have solved the problem of program correctness. Thank you for listening to my talk. Okay, maybe not. But for sure, these languages have made it much simpler to write correct code. And what we're going to argue here, and I don't think for a lot of the people I can see here in the audience, that's not news. But these languages also have made it easier to verify code. So this work and this talk is about hybrid verification. The goal is to leverage the nice parts of Rust while still verifying the less nice parts, and then we can do both more efficiently because of the nice parts. So I'm going to go into the what, the why, and the how in order. But this is a high-level talk. I'm not going to go into technical details. If you want more details, please go and read the paper. So this is a Rust code base. And all the green here is safe code, and the red here is unsafe code. And there's not so much unsafe code, but the goal of hybrid verification is to separate the work between safe Rust verification and unsafe Rust verification. For the safe Rust verification, we use Proza, mainly because Xavier is an author of the paper, but also because we have the meta theory to support it. And then what we do is that we have a layer of abstraction in between. In Rust, it's usually just saying the function is safe, but for verification, we have a hybrid specification at the boundary between safe and unsafe. And the goal is that the tool that verifies unsafe code and the tool that verifies safe code should both understand this hybrid specification. So because there was no tool at the time for unsafe Rust verification, we started developing Jillian Rust. There's now a few other tools, including Refine Rust, but I believe that still none of the existing tools quite satisfy this constraint that they can interpret specifications used in a safe tool. So that's the what. Let's talk about the why, and to talk about the why, we first need to talk about safe Rust verification, which is not quite the theme of the paper, but we need to go through that. So take this function here. It's quite simple, but really if you wanted to verify this, it's a lot of work because this receives a mutable reference to a vector, and it also receives a function, so it's a higher order function. It receives another function as a parameter. That function is an FN mute, meaning it can modify its environment. If it captures, it's a closure, so if it captures something in the environment, it can modify it. It also receives the mutable reference to a U32. And at the end, we check this. So it's very simple. It takes a snapshot of the first element of the vector. It modifies the second element of the vector, and it checks that the first element hasn't changed. This is automatic in most of the safe Rust verifiers. If it's not fully automatic, it's because some features are not supported, but in principle, it's mostly automatic. Safe Rust, and if you want more, you can add annotations for more functional correctness properties. The history of safe Rust verification started with Prusty from Peter Muller's group, mainly by Vaitotas. And they realized that you could basically automatically encode in separation logic the proof done by the borrow checker to get to a high level. And that would mostly automate a lot of the proof work done by that you need to do. Then Rusthorn and Rusthornbelt and Crusoe, they figured out you can have just a pure first-order logic encoding, just removing the separation logic entirely. Then Eneas, that you've heard about from Leo's keynote earlier, realized you can have actually pure executable encoding of safe Rust programs. And finally, Flux is a more lightweight approach in liquid type. So they don't have all the same expressivity and so on and same automations, but more or less they capture this idea that having safe Rust, you can much simplify the proofs. Now, does anybody here do C verification? And can you try and imagine what it would take to verify the same code in C? Just first of all, it's higher order. There's not that many tools that can verify this. I mean, take real C code and verify it. That's not going to be easy. And it's going to be even harder because actually this does not hold. Because this modify function could be doing unrestricted pointer arithmetics, and it could go back in the vector and modify the first element. So it just does not hold in the first place. So what this says is that when Rust users, normal developers, write function signatures, what they actually do is they write separation logic specifications. That's not a new insight. That's from Ralph's work on Rustbelt. But what this says is that in this new era, people change the way they write code, and for you, they write some specifications, some separation logic specifications. Can you believe that? The catch is they do it at a cost. They will only do it if sometimes they can say, I don't want to do it. So, all these languages have an unsafe counterpart, and in unsafe Rust, you can just write Rust that doesn't have all the safeguards as usual. And there's a catch also, because in the code I showed earlier, one of the things I do is take a mutable reference to the second element of the vector, and that is what we call internally unsafe. So in apparent, it's safe, but the implementation of that operation is implemented using unsafe code. So that's annoying, because if you get this wrong, then you could break basically all the type system properties given to you by the language. That breaks basically everything you've proven about the safe code. It's quite hard to verify. I'm not going to go into details, but this function here returns a mutable reference. So it returns kind of a promise that whatever you do with that mutable reference, you're never, ever going to break the invariant of the vector itself. But the good thing is that there's only 2% of the code or around that's unsafe, and it's all behind what we call safe encapsulation. So there's this boundary between safe and unsafe code, and supposedly if you check at the boundary, then you're fine. Hence hybrid verification. The goal is if instead of putting a lot of effort on the entire code base, you put a small amount of effort on the safe code and a lot of effort on the unsafe code. And that includes, I don't know, I showed a simple example, but tools like Proza can verify higher order iterator function doing crazy stuff, and they will do it with little help compared to what you would need in something like C. Taking a breath. We've seen the what, we've seen the why. Let's talk about the how. So we've put these two tools together, Gillian Rust and Crusoe, and then a bunch of meta theory that people who are much more clever than me did. And specifically, we use Crusoe because there was meta theory to back up the soundness of Crusoe using separation logic and connecting it to Rustbelt. And then we built this new thing based on Gillian. So I'm going to give a very, very quick introduction to Gillian. Gillian is what we call computational symbolic execution. There's other tools that do similar things. Viper, CN, Javert, very fast before that. The specificity of Gillian is that it's parametric, meaning when you want to create a new tool based on Gillian, you kind of explain to the tool, you implement symbolic actions and core predicates, which form the basic operations of your state and the basic block of the separation logic you want to use. We've instantiated it for these languages, but interestingly for Rust, the kind of new, kind of exotic state updates we get are, for example, allocating lifetimes, and the new kind of core predicates we get are, for example, lifetime tokens or prophecy observations or things like this. So GNRust is a lot of new things that are described in the paper. I'm not going to go into details into everything, but we have a new kind of symbolic heap model to automate heap operations that includes normal Rust stuff, but also when you need to do pointer arithmetics, it will kind of try and automate that specifically for array reasoning, vectors, and all that. We encode the lifetime logic, and we importantly bring new automations that are specific to how CSE, compositional execution, operates. We have encoding and automation of some prophecy reasoning, and also the most important part for me is this front end that takes Proza specifications and compiles them to separation logic specifications. And the way it works and what makes everything work is that Crusoe, for example, when you talk about a vector, when you talk about a linked list, it can only see an abstraction of it. Crusoe, when you talk about a vector, you say, I push at the end of a vector. Before that, I have some sequence of data. And after that, I have some sequence of data with an element at the end. And that allows you to reason very efficiently at the abstraction level. And Y3, on which Crusoe is based, can reason very efficiently about this. Unfortunately, if you want to reason about unsafe Rust and you want to reason about the implementation of the vector or the implementation of a linked list, then you actually do need to think about the pointers and the separation logic that's there. So GNRust has that view, can reason at that level. And what works is this interface where you can convert from one level of abstraction to the other. Again, that's not really a new insight. That was Rust Belt and Rust Front Belt, mostly Rust Front Belt for that one. But what's new here is that we actually have two tools that are able to think at those two level abstractions and work together. And this is really what makes hybrid verification real. I don't know how long I've taken, a bit in advance, but I'll still talk about the last ingredient, which is targeted automations for unsafe Rust verification. And this is made possible by two things. First of all, we have Jillian, and in Jillian we can encode these automations. And second, we have hybrid verification, which means most tools, if you have to think 99% of the time about safe Rust and 1% of the time about unsafe Rust, then probably the unsafe Rust automations are not going to be very good. But here, because we have hybrid automation, because we split the work, we can let Crusoe think about how to automate safe Rust verification, and we can think about unsafe Rust verification. And we can make those automations work for the cases we know happen. There's rarely any very higher order function happening in unsafe. There's some, but most of it is just manipulating a bit of pointers around, and we need to do that efficiently and mostly automatically. So for example, this is the real code from the standard library of what vec_push is. So it's just adding an element at the end of a vector. This is the real Crusoe specification of vec_push. It's missing a precondition about the length of the vector because you don't want to overflow your integers and so on, but it's not very important. And to verify this, almost automatically, Jillian does a lot of things for you. First of all, there's this notion of opening and closing borrows. So you need to think about the invariant behind your mutable reference, and you need to open that invariant and close that invariant. We've designed new automations to do that, and so Jillian can do it fully automatically, and if it cannot, you can still ask to do it manually, but most of the time it will do it automatically. In Jillian, if you don't have a specification for a function, you don't need to specify it. Most of the internal grungy functions like razor for push don't have really a nice specification. You can specify them, but it would be difficult and painful. Here, we'll just symbolically execute it in all cases that we encounter, and if it works, and it's still sound. We have pointer arithmetics. As I said, our symbolic heap model can automate a lot of the reasoning about arrays, and here you add an element, it might have reallocated, and so on. It's a bit grungy, but really it's not that difficult to automate because really it's not that hard. It's just a lot of cases, so you need something that goes fast. And here, GNRust is not fully able to conclude the proof. You need to tell it to there's a prophecy variable going on. You need to say something about what happens when the lifetime ends. And here we have one line of annotation for the whole proof, asking GNRust to resolve that prophecy and assert that you're done with the mutable reference. Once that proof is checked, then you never have to think about it again from the Proza point of view. You know that push is just something that takes a sequence of data and adds something at the end. What we're pretty proud of is that this takes less than 3 seconds to verify. This is some orders of magnitude faster than things that have been done before, with a lot of trade-offs, obviously. And so, wow, this is amazing. We have many, many limitations. I'm not going to list all of them. We probably have more that we haven't thought about. We haven't used the tool to a huge extent, but for what we've used it so far, it worked pretty well. I think what I want to say from this slide, which is a pre-takeaway, is that Gene and Rust isn't really a production-ready tool. I'm not telling you if you use it tomorrow in your company, you can instantly verify all your code base, and then you get all the guarantees of Crusoe also after that. It would be great if we were at this stage, but it's not ready yet. It's a prototype. What we wanted to do is show the feasibility of this hybrid approach, and we managed to do that. So for me, hybrid verification is the real takeaway of the work. Now, I see my PhD supervisor looking at me like, why are you saying this? Here's a post-pre-takeaway. We did pretty good. We did have new automations. We did prove new things from the standard library. And for the things that were already proven by other people, we went a few orders of magnitude faster. So, and with less automations. So we did pretty good. There is a trade-off, of course. We're not foundational. We rely on CD solvers. We rely on Jillian. But overall, it's a pretty good tool. And if development continues, I think it can be quite impactful. So after the pre-takeaway and the post-pre-takeaway, we can move on to the takeaway. The takeaways are hybrid verification is good. Yes, hybrid verification is good. 98% is, I would say, boring on the separation logic level. You want to do the boring thing and verify really the properties you care about. And for that, you want to use a safe Rust verifier. And for the 2% of unsafe code, you really want those automations and those tail automations. And this is what hybrid verification gives you. Thank you very much.
Okay, we have time for maybe 1 or 2 quick questions.
Hi. So I noticed that one thing you probably didn't mention, but one thing I noticed, you've actually verified get unchecked mute. So is it correct to understand that you extended Crusoe to also support specs for unsafe functions?
Not Crusoe directly, but Jillian Rust verifies the specification used by Crusoe. So in a sense, we provide the guarantees that Crusoe needs for unsafe code, yes.
Okay, thank you.
Cool talk. I'm wondering how you think this compares to something like Varus that allows you also to mix safe and unsafe with ghost linear types and so on.
So yeah, so Varus is one of the coolest tools out there. Currently, at least, Varus has a proof-oriented programming approach. So if you want to verify a linked list, you kind of need to implement it using the Varus primitives or using the Varus standard library. So even though Varus has made progress trying to actually verify things from the real standard library of Rust, I don't think, last time I asked Andrea, he confirmed that currently Varus wouldn't be able to verify what we verified in the standard library. But it's just, for me, a different approach. And if everybody could do proof-oriented programming, I would be much happier in my life. But I think Varus is really cool. It's just different targets.
Okay, so let's thank the speaker again. So next we have Kimaya, who's telling us about scheduling.
Okay, can you hear me? Yes? Okay. Hello everyone, I'm Kimaya Bedarkar, and today I'll be talking about refined Proza. This is a joint work with some amazing people at MPISWS. So our work combines advances in program verification and real-time systems to prove end-to-end timing guarantees on a real-time system scheduler. So real-time systems, or for short RTS, generally refer to these kind of systems that are deployed in some sort of cyber-physical environment and that are subject to strict timing constraints. So for example, if you think of the system in a car, this system is required to pop its airbags immediately on sensing some sort of sudden deceleration. And as shown by this example, RTS are generally deployed in some safety critical environments where failures can be very costly. So the correctness of the systems has been quite widely studied. And in particular, the abstraction that we are looking at here is as follows. So you have some non-deterministic environment, and this environment is sending some inputs to the real-time systems. Now inside the RTS, there is a scheduler and a processor, and the scheduler must decide how to respond to this input, and in response, it dispatches some code to be run on the processor, which we usually call as executing a job. Once this job finishes, control is transferred back to the scheduler, and this process continues. Now, the property that we are interested in these sort of things is what we want to do what is called a response time analysis, in which we want to relate the workload that the system is processing with the response times exhibited by the processor. So by response time here, I mean the interval between a job arriving into the system and finishing. And when I say the workload here, I mean how much workload the system is supposed to handle, which is usually characterized by a maximum rate of arrivals of the jobs into the system, also called the arrival curve, and the maximum cost of execution of each job given by a worst case execution time. So to analyze these kind of systems, what we usually do is we start with the concrete implementation of the system. So for example, let's say we are analyzing the system in a car, and then we create some abstract system model that hides all implementation specific details and only focuses on the timing behavior of the system. Response time analysis then focuses on mathematically analyzing the abstract model to prove these kind of bounds on the response times. So this field itself is an old field, but newer advances in this area have focused on the use of theorem provers to analyze the correctness of this response time analysis via the use of theorem provers such as ROC. For those of you who don't know, ROC is an interactive theorem prover which gives us very high assurances. And in the past at MDISWS, I, with some of my colleagues, have worked on Proza. Proza is this ROC-based library of formal schedulable response time analysis. Now, the very nice thing about Proza is that it makes sure that the analysis itself is completely free of errors, which is especially valuable in the safety critical domains. But the wrong modeling of the system itself can still potentially be a source of errors. This is the gap that we address in this paper, and in particular, our approach is to use program verification to prove that a concrete system implementation refines its abstract system model. So there has been some work along these lines in the past, and to set context for the previous work and what we do, I would like to differentiate between interrupt-driven schedulers and interrupt-free schedulers. So the main notable thing about interrupt-free schedulers is that all time is divided into these quanta, and at the beginning of every quanta, a scheduler is invoked. The scheduler makes a decision on what happens in that quantum. So because of this, analyzing these systems is kind of natural in the sense that proving the correctness of this scheduler amounts to showing that the scheduler makes the right decision at every point, and then the timing analysis is kind of separate from the functional property of the scheduler. Moreover, in these kinds of systems, it's a bit easier to analyze the system overheads. So by system overheads here, I mean all the processing time that is not given to external workloads, but to the scheduler itself for doing tasks such as deciding which task gets serviced next. So because these overheads are only in the beginning of the quantum, we can kind of abstractly reason about them by assuming that not the entire quantum, but only a part of it is available for external workload. Indeed, this is the approach that has been used in the past, especially in the work by the Certicos team. In their work, they combined Proza with the real-time extension of the Certicos kernel and proved the timing correctness of their interrupt-driven schedulers. In our work, we want to move beyond interrupt-driven systems and look at interrupt-free systems. In interrupt-free schedulers, there is no such notion of time quanta. Because of this, it's not clear how to express the timing correctness of the system as a functional property that we can verify using program verification. Moreover, in these systems, the scheduler doesn't get control periodically, but only when the executing job finishes. And because of this, if the scheduler gets back control after a long time, there might be a sudden burst of overheads where the system needs to do a lot of work, and it's hard to account for these. So why do we want to look at interrupt-free schedulers? It's because they're actually quite common in practice. So because they do not require any software or hardware implementation of interrupts, they are quite energy efficient, which makes them ideal for deeply embedded systems, which can be often energy constrained. So for example, the Tangi operating system and TinyOS, both of which are operating system for Internet of Things, use interrupt-free schedulers by default. At the other end of the spectrum, the ROS2 middleware also uses interrupt-free schedulers for its in-process executors. So the question that we want to answer is how can we verify the timing properties of a concrete implementation of an interrupt-free real-time system. To answer this question, we present Refined Proza. Refined Proza combines two tools, Refined C, an iris-based C verification tool, and Proza, a ROC-based library of response time analysis. Now both Refined C and Proza are ROC-based tools. Consequently, all of our results are also formalized in ROC, giving us very high assurances. So let us look at what we do. To illustrate our proof methodology, we have verified Russell. Russell is a scheduler written by us in C. It's about 400 lines of code, and it's roughly similar to ROS2's default executor. And the property that we want to prove about Russell is that based on some assumptions about the workload, response times shown by Russell are bounded. Now, to aid in our task, we have some pre-existing tools. So first, we have Proza that I mentioned before. And what Proza does is that given the abstract system model of a system which is usually represented as this infinite time traces of execution with some invariants on it, Proza gives you tools to prove that response times are bounded. On the other end, we have Refined C. Given some piece of C code, Refined C allows you to prove functional specifications for this code, usually in the form of pre and post conditions. Now, the problem is that these two things are quite different in that C, and by extension Refined C, has no notion of timing, but to invoke Proza, we need to prove some timing properties. So how do we even reason about timing in an untimed language? To solve this problem, what we do is that first, we divide up Russell into this like sequence of basic actions, where each basic action corresponds to one thing done by the processor, such as reading one job from the sockets or dispatching one job and so on. These basic actions are then reflected into the code of Russell by the use of so-called marker functions. These are basically ghost code and don't really affect the execution of Russell itself, but they mark the sections belonging to each basic action. And then we use Refined C to prove functional invariants on the trace of marker functions. At this point, we have not modified C or Refined C in any way. There is no timing involved yet. So next, to give timing behavior to our system, we associate with a list of marker functions, a list of timestamps. And the idea is that each timestamp is giving you the instant at which that marker function was triggered. We want to consider all possible timing behaviors, so the list of timestamps is universally quantified. But we don't actually want to consider all possible timing behaviors. We want to rule out things which we can't actually observe at runtimes, as well as encode some assumptions about how much workload is in the system. So we define some notion of validity of timestamps. Then we combine these timing properties that we assume with the functional invariants we get from Refined C to get timing and functional invariants. At this point, we would like to invoke Refined C and get to our end result. But this is where we face our second challenge, which is that real systems rarely behave ideally. In case of Russell, this manifests as having to reason about system overheads. Recall that system overheads is all processing time not given to external tasks, but to the scheduler itself. To tackle this problem, we extend Proza with a new overhead-aware response time analysis for the abstract system model of Russell. Now in the rest of the talk, I'll go in detail of some of these steps. Let us first start by looking at at Russell and what we prove about Russell with Refined C. So to give you an idea of what Russell does, I have here the main scheduling loop of Russell. And what it does, so Russell has some sockets associated with it, and it starts by first checking all these sockets and reading all the messages that have arrived on these sockets. Then each message is statically associated with the priority level, and Russell picks the highest priority pending message. Of course, it can be that there are no pending messages, in which case the loop continues. In case there is a message to be processed, each message is associated with a callback function. This callback function is dispatched. The callback function executes. When it finishes, control is returned to the scheduler, and the loop continues. Now, the property that we want to prove about Russell is that the time between a message arriving into the system and the callback function of the message finishing is bounded. This is what we call the response time, and you can see here that the response time consists not only of the callback function of M, but also the system overheads, in this case the selection and dispatch overhead. Moreover, here I only show the simple case where M is immediately selected for execution as soon as it arrives, but more realistically there might be higher priority pending messages, in which case the response time includes the time for the callback function of those messages, as well as overheads associated with those functions. So, to reason about Russell, I said that we divide Russell into this sequence of basic actions. In this case, the basic actions are shown here, and the marker functions are shown here highlighted. And each marker function marks the beginning of a new basic action. Sorry, do I have only 3 minutes left?
Last question.
Okay. So now we want to capture all the functional properties of Russell as invariants on the trace of marker functions. So we use refined C to do this, and in particular, the properties that we want to prove is, the first one is a kind of an obvious property. We want to focus on the scheduling algorithm of Russell itself. So we prove that the picked message has the highest priority. And analogously, if no message is picked, that's only because there are no pending messages, which involves having to prove some data structures used in the scheduler state. For us, this includes stuff like bitmaps and queues and so on. The second property is a bit more abstract. We need to prove that the marker functions follow a specific sequence. This is required to show that all system overheads can be associated with one job. And to do this, we need to do some trace reasoning in refined C. Next, I'll show you how we think about the timing behavior. So I told you already that each execution of Russell goes through some basic actions. These are indicated by marker functions, which are associated with some timestamps that are universally quantified. Now, these timestamps induce some runtimes. And since these runtimes are eventually going to be part of response time of some message, if they run unboundedly, of course, the response time won't be bounded. So we placed our marker functions such that each basic action does not contain any unbounded loops, in which case we could use some static analysis tool or even just measure at runtime the worst case execution time of each basic action. And then the validity of timestamps requires the runtime to be bounded by the worst case execution time. We have not computed the worst case execution times for Russell, but we believe this can be easily done. Finally, now that we have the functional properties and timing properties, we can state our final theorem. We take some trace of Russell, then we associate with it a list of timestamps, and we require this list of timestamps to be valid. The notion of validity here includes this wset property that I talked about, as well as some bounds on the rate at which workload comes into the system. If this validity property holds, then we show that the response times are bounded. This is a very high level view of the proof. We start with some trace of Russell, then we use refined C to prove that this is a valid trace. We take the valid timestamps property, and then we combine these two properties in our extension of Proza to prove that the response times are bounded. With this, I'm almost at the end, but before I conclude, I would like to mention the Variarty. Variarty was published at POPL this year, and it proves some timing properties for distributed systems. The common thing between us and them is that they also have to answer this question of how to deal with timing, especially in the context of verification, which is usually untimed. Interestingly, they also end up making the same assumption, which is that code sections are bounded by some wset. The difference is in how these assumptions are encoded. We focus on not touching the semantics of C or modifying refined C, but in Variarty, time is actually tracked in the semantics, and each event non-deterministically generates a timestamp, which is assumed to obey this wsets, and then the rest of the approach works in a verification-based way. Because of the way they model time, they get the flexibility of modeling time-based branching, which we cannot, but we also do not require it, and so we have not explored if this approach applies to us yet. So with that, I would like to conclude. Today I've talked about refined Proza, which contains a formally verified response time analysis for an interrupt-free scheduler implementation. In getting to our end goal, we showed how to handle timing without changing the language semantics. And we also show how to incorporate scheduler overheads into the timing analysis of the system. Admittedly, I did not have much time to go into the scheduler overheads part today or the response time analysis in general. But all the details of all of this, as well as how exactly we use refined C and what properties we prove, are included in our paper. The paper, the appendix, and the rock formalization are available at this link. Thank you for your attention, and I'm open to questions.
Thank you for your talk. Did you try to run some real programs, real task sequences, and see how big is the difference between the expected time and the real time?
We have not yet done an evaluation to measure the tightness of the bounds, but it's definitely on the horizon.
Hi, great talk. Thank you very much. Did you have to extend refined C in any novel or interesting way to be able to do all of this?
Not really. Refined C worked really well. I mean, of course, to do the trace reasoning, you kind of have to modify how the whole setup works a little bit, like you have to generate these events in the semantic steps, but no major things, just maybe adding a few ghost theories or so.
Cool, thank you.
Hi, I'm Jenga Lee from Kite. So I have a bit of a technical question. So as far as I remember, refined C only supported safety reasoning, so it cannot really prove that any program terminates. So does that mean in theory, so you did not have any criteria that your scheduler actually proves a valid trace?
So the scheduler does not terminate. The scheduler is an infinite loop, and we do not prove, and nor does it hold that the scheduler terminates. The response times are like some section of the infinite loop itself. So all we need is safety reasoning. We just need to know that the valid trace property is never violated in the
So I was wondering, is like, do you prove anybody that after some time a trace actually appears?
No, I mean it's kind of like the way the theorem is stated is that if this trace is a trace of refined C, then it's a valid trace. This is the adequacy that we get from refined C. Thank you.
Okay, so we're actually right on time. So let's continue with Gaga, who is telling us about certified compilers a la carte. And also, let's thank the speaker again and the welcome new speaker.
Okay, so I'm going to talk about how to make certified compilers more extensible and modular. So it's joint work with Ian, Ender, Arthur, Charles, and Ijo from Waterloo. So certified compilers are a critical piece of software. And application developers who write the software in high-level language using the compiler to transform that code into instructions that the machine can understand. But there's a bug in the compiler. Okay. Now this bug in the compiler, this completely invalidates application level guarantees. This bug in the compiler is completely invalidates the application level guarantees, right? And it's not just a hypothetical situation. Real-world compilers like Clang and GCC have open bugs. And one way to eliminate bugs in compilers is by proving it correct. Compilers that are proven correct are called certified compilers. And these compilers eliminate an entire class of bug in the critical parts of the software stack. Now the problem is that certified compilers are not cheap. Aside from the inherent difficulty of constructing mathematical proofs, extending, maintaining, and evolving compilers are difficult. Certified compilers are difficult. And this is a real problem because as language evolves, the compiler needs to evolve as well. So to see this in practice, let's look at a real world, let's look at a toy example of a certified compiler. So let's build a certified compiler for IMP. The first thing we do, We have our source language, which is just a simple imperative language. So we have semantics for the source language. Then we give you target language, which is a stack-based virtual machine instruction set. We give semantics to the instruction set. And then write a simple compilation function, which is a recursion over the source language. And then prove is correct. Now the problem here is that when we want to extend imp with new features, for example, switch statements, loops, and heaps, we have to duplicate the code. And this copy and paste is antithetical to good engineering practices. Now it creates tedium, obstruct changes, and collapse separation. And this is not just a new problem. It's an old problem in a new setting. And in particular, this is the expression problem. So the expression problem was posed in the late 90s by Philip Wadler, and it says that, so basically we want a data type, I want to extend data with new cases, I want to have functions over data type, and extend the function with new cases as well. And they want to do so without recompiling code. I want to maintain type safety. So the goal is kind of ambitious here. But in setting of proof engineering, it's a different case. So we have inductive types. I want to extend inductive type with new cases. We have inductive proof. I want to extend inductive proof with new cases. And then I want to do so without recompiling proofs. I want to maintain logical consistency in the proof assistant. And this is not just academic curiosity. Real-world languages and real-world systems prioritize extensibility and modularity. So for example, we have RISC-V, which is a modular instruction set architecture. So in RISC-V, there's a base ISA, and then we have other extensions like vector instructions and multiply instructions. Another example is MLIR. MLIR is a compiler infrastructure that enables extensible domain-specific compilers. Okay. Now, in the case of certified compiler, this problem is even more pressing because we have code and we have proof. And last year's PLDI Keynote, we have Magnus Marin here, who is the author of KML certified compiler, and he's talking about the need for extensibility and reuse in certified compiler and in proof engineering projects for certified compilers. And also in ComSets, they have noted the copy and paste between IRs and semantics for IRs in ComSets, in the code base of ComSets. And the same thing for KML. They talk about needing a readable diff infrastructure for KML. So the summary here is that we want modular IRs, we want modular parses, we want to cut redundancy and boost clarity between these IRs and certified compilers. So to reiterate, we want reusable intermediate representations, we want reusable passes, and we want reusable compiler extensions. So the goal is kind of ambitious here. So how can we do this? So in this work, we're taking a fresh look at programming. In particular, we're inspired by object-oriented techniques of inheritance and family polymorphism. So basically what we do here is we retrofit family polymorphism and inheritance into the ROC prover to enable extensible proofs. So this is implemented as a plugin for ROC today. Okay, let's see how Rocket can solve the expression problem. In particular, we want to do composition and extensibility of certified compilers. So here's imp. In Rockets, modules are called families. So we have something called a unit of extensibility called family. And if we want to extend Rocket with switch, heap, and loop, we do this in a refinement called the trait. And notice here that we don't duplicate the code here. We just extend it modularly. And then we can compose it together to form a new certified compiler. And Rocket is just a simple one-liner. Right? So there's no code duplication, there's no proof duplication, and then there's composition and without proof rechecking. And we also maintain logical consistency. Okay. Let's see the key ingredients of Rockets that enables this kind of reuse. So the first thing is something called F-inductive. So in Rock today, inductive types are close to extension, which means that once you have an inductive type, for example, this command here, you can't extend it. But in Rocket, we support something called F-inductive, which allows extensible inductive types. So the loop trait, for example, can inherit and reuse the previously defined cases without rechecking them. Then you can also define modular additions to the inductive cases. So in Rock today, recursion and fixed point and pattern matching is also close to extension. So what we do in Rocket, we have something called F recursion that allows us to extend and reuse cases of recursion and pattern matching. So have like the compilation function here, and we can reuse these cases without rechecking them, and we can modularly extend it to support new cases. So the last ingredient here is something called F induction. So inductive proofs in Rock as well are close to extension. And what we do in Rocket is that we can have something called F-inductive, where you prove cases, and then we can reuse those cases just like F-recursion and F-inductive. And the key idea behind Rocket is this. Every family member is an implicit extensibility hook, which means that the meaning of a family member is late bound, is not hard-coded to the particular family it is in. And aside from F-inductive and F-induction and F-recursion, nested families are also implicit extensibility hooks, which means that if you have a nested family called IL, which represents an intermediate representation, is also late bound. So the meaning of IL is not hard-coded to the IM family. So nested families are late bound. So let's see how this late binding can help us in modular IRs and ILs and passes. So imagine we have an underpass compiler that compiles IL1 to IL4. So in the first pass, we're removing some feature X, we're removing some feature Y, we're removing some feature Z, and we're adding some constraint W at the end. So clearly, because these passes are very similar, they share some common structure between the IRs and the passes between them. So in Rocket, we can have a base compiler, base IL rather, that have a common component and common semantics of these ILs, and then the other ILs can reuse the common components. And then we can have a base transformation, and then the other transformations can reuse the common component. And then one cool thing Rocket can do is because of late binding, we can compose extensions. We can compose the passes together and get a fusion, which is just a single tree traversal. So we avoid long compilation time through late binding of the S families. Okay, we've seen Rocket so far. We've seen how Rocket brings extensibility and reuse certified compilers. We've seen the key ingredients that brings about Rocket's expressive power. So let's see how Rocket works. So we know from OOP theory that the essence of inheritance is self-parameterization. So what we do in our implementation is that we compile the implicit extensibility hooks in Rocket to explicit self-parameterized modules in Rock. So basically, we follow this principle quite literally. And then our compilation is also incremental to support interactive theory improving in Rock. So let's take a look at an example. So here, for illustration purposes, I've nested the com inside a nested family called IL. So we can see that we compile this IL, and we have two parameters which represent how nested it is in the family. So we have parameters that represent the self-parameterization of each family. And I'll do a similar thing for F recursion, and do a similar thing as we compile the function. So one important thing here to note is that the self-parameter represents the typing context of a family. The typing context is the previously defined cases of a family, and this allows us to have a well-founded open fixed point when computing the fixed point. So here's what we do. When we close the family, we reuse all the cases and we take a well-founded fixed point of these self-parameters. So previously, we mentioned that we compose extensions in Rocket without code duplication. So let's see how that works. So take this extension we've developed, and then we'll compile each extension's compilation function into a parameterized module. And then when we want to compose them together, we use the work to include mechanism. So this way, we reuse the code that we've previously generated without recompilation and rechecking proofs. So we've seen the language design of Rockets. We've seen how Rocket works. Let's try and scale Rocket to a larger proof engineering project. So in particular, I want to scale it to a composition and extensibility of certified compiler project. So let's start with our base imp compiler. Then we'll extend it with different features. For example, extend it with heap, switch, loop, external calls, intrinsic calls, function calls, structures, and union. And then we can compose these features together to get a compiler for an imperative language with all these features together. And it so happens that this compiler is ComCert. And this is intentional because we refactored ComCert to make sure each of these features is modular. So we've taken ComCert passes. So in the first pass of ComCert from C to C lights, we made it to be nano passes, and then we compose them back together. In the IRs of ComCert, we have some reuse there between common ILs and common passes. In the backend of ComCert, we also have some reuse between Mac and linear IR. And in the ISA, we faithfully modeled the RISC-V modular semantics in our case study. So Rocket addresses cost-cutting demands for modularity. So we've seen how Rocket does this. So let's look at some metrics about how we quantify this proof and code reuse. So basically, we want to measure the amount of code and proof in terms of lines that it takes to build the base certified compiler and compiler extensions. So for the base compiler, we write it in Rock and write it in Rocket, and we compare the lines of code. So here we can see that the compiler in Rock is less than the compiler in Rocket. So this is some setup about F induction and F inductive in Rocket there. And then for other extensions, you can see that the amount of code it takes to write in Rocket is significantly less than Rock. So this is because of there's no copy and paste in Rocket, and we have some lot of modularity between passes and ILs in the compiler. So Rocket is a generalization of a previous work called FPOP. So FPOP adds an inheritance mechanism to Rock to enable composable and extensible STLC meta theories. So the key generalization of FPOP is that we support nested families. So FPOP is more expressive. So Rocket is more expressive than FPOP, so we can scale from an STLC meta theory into a certified compiler like Rocket. Another thing where Rocket shines is that Rocket is 18 times faster than FPOP because of some performance improvements we do. Okay, so it has some limitations as well. So Rocket is currently slower than Rock. We need some more proof automation, and we need some more language features like extensible records. So we've seen language design and implementation of Rocket. We've seen the expressive power afforded by Rocket, how we allows the monolithic certified compiler to be modularized. So our design of Rocket was guided by a real and important use case, which is the construction of certified compilers. Proof compilation is fast, which makes Rocket a practical tool. So we hope that this will be a step towards large-scale modularity in the PL community. Thank you.
Okay, so we have time for some questions. Please come up to the mic.
Actually, I have a question myself. So I guess so here you use modules to solve the expression problem, right? And then so in the data types a la carte paper by Philip Wadler, they solve it with type classes with minimal metaprogramming overhead. So I wonder how would you compare your approach to their solution with type classes?
So there are two solutions in general to expression problem. So the first class of solutions is linguistic solutions, and second class solution is like library solutions. So linguistic solutions add new features to languages to support and solve the expression problems. So library solutions use the machinery already present in the language to solve the expression problem. So I think it's a trade-off about how you want to solve your problems. So as PL researcher, I think linguistic solutions are more elegant.
But Koch has both module system and the type classes. Do you try solving this with type classes?
So it's just about abstraction, right? So we want a higher level of abstractions, in particular inheritance. So inheritance, we can do things in a straightforward way and say this extends this thing, and then it's straightforward, right?
Okay, thank you.
Hi, so I actually have two questions. The first question is I wanted to ask about the proof experience. So can we prove it like directly at the level of Rocket, or will we need to compile it to Rock first and then prove with it?
Yeah, so prove directly in Rocket. So because our compilation is incremental, we're on par with Rock as well.
So can you do like structural induction directly on F inductives?
So F inductive does that for you.
Oh, okay. And the second question, have you tried benchmarking your refactored compiler? How does it compare to the original compiler in terms of speed?
Yeah, so because of narrow pass fusion, we recover the same performance back. So you can check more about it in the paper.
Thank you.
So how do you verify that like your different, this is a very modular system. How do you verify like the different features you're going to add modularly don't like interact with each other in a negative way that like invalidates some of the proofs you'd want to make about the language?
Okay, that's actually a very good question. So in OOP terms, this thing is called feature interaction, right? So when there's feature interaction, Rocket generates new proof obligations for you to prove. So for example, if you're doing STLC and you combine like a fixed point and ISO recursion, it generates new proof obligations for you to prove.
It's really cool stuff. I was wondering, your examples, does it also support extensibility of arbitrary inductive families with indexing and everything?
Okay, we don't support indexed inductive types.
So it's extensibility typically the syntax of the language, not necessarily of some relation over it?
Okay, actually, we support nested inductive type, but we don't support, so we support index inductive type, but we don't support parameterized inductive types. So I know parameterized inductive types can be simulated by index inductive types.
Usually at the loss of a universe level, right?
Yeah, yeah.
Is that ever a problem?
In our case study, we don't run into any problems about that.
Okay.
I have a question also. In the presentation we saw yesterday by Owen, he showed how he extended an existing compiler, Bedrock 2 compiler, by adding leakage traces. So that's an additional state element. Whereas in your presentation, you were only showing the addition of cases to inductives. But could your approach also support the addition of new state to the semantics?
So I guess states are represented by like a record, right?
Yes, exactly.
So that would require like a new language feature to have extensible records. But it's possible with polymorphism.
But that's future work?
Yeah, future work.
Nice. Do you have more? Simon, you can already set up, but while Simon is setting up, we can also take more questions if there are. Otherwise, yeah, let's thank the speaker again. So next we have Simon, who is telling us about destabilizing iris.
Hi, can you all hear me? Great. I'm Simon, and today I'm going to show you how we brought a key feature of the Viper verifier family, namely heap-dependent expression assertions, to Iris. And as we will see later in the talk, this required us to make some quite fundamental changes to Iris. This is joint work with Nicholas, Howie, Michael, Andrea, Peter, and Derek. I want to start with a question. How do you reason about large stateful programs? The challenge here is that if you think about a larger program and you decompose it into its individual parts, then one part of the program, such as the function b up here, can modify the state, say store 41 in the location L, and a totally different part of the program, such as the function h down here, can observe these modifications. So everything is implicitly connected via the shared state, which makes reasoning about these programs more difficult. One popular answer to this question over the last 10, 20 years has been separation logic, because separation logic enables modular verification of stateful code. What that means is we can verify our code function by function, even if it involves pointers, references, and so on. And the key feature of separation logic that enables this is ownership reasoning. Assertions in separation not only describe the contents of memory, they also carry with them ownership that allows us to access or modify that memory. And we can see this quite clearly in the specification for the function b from the previous slide. It first of all tells us that we update L from an arbitrary value to 41, but it also tells us a little bit more. It tells us that b only accesses L and no other locations, because it only gets ownership for L in the precondition. And one separation logic that has been particularly popular over the last couple of years is the separation logic framework Iris, which you can use for all kinds of verification, including fine-grained concurrency verification, multi-language verification, and for developing semantic models of type systems, and much more. But, shocker, separation logic is not the only foundation for ownership reasoning, and Iris is not the only tool out there. Another quite powerful approach for ownership reasoning is implicit dynamic frames, which has been used quite successfully by the Viper verifier family, which includes Viper itself and also several frontends, such as Nagini for verifying Python code, Gopra for verifying Go code, and Prusty for verifying Rust code. And we can see the differences between these two approaches quite clearly if we put them side by side. In separation logic, we typically reason about resources, such as L points to B, which combine together ownership with knowledge about the contents of memory. in implicit dynamic frames, the foundation of Viper, these two are separate. We have access predicates to reason about ownership, and heap-dependent expression assertions to reason about the contents of memory using program expressions. And I want to focus on these heap-dependent expression assertions. They are somewhat of a strange animal if you have a separation logic perspective. They assert facts about the contents of memory without asserting ownership for that memory. And when I first saw this, I was a bit confused, I have to say. So I started wondering, well, like, why would you want heap-dependent expression assertions in the first place? And also, like, how do they work? And slightly differently, well, can we usefully integrate them into separation logic and into Iris in particular? I'm now going to first focus on the first question, and then in the rest of this talk, we will explore the second question. Now, to answer the first question, I've brought along a little example here. In this example, we have a produce buffer function that produces a buffer B, and then later on we will call a read-only client that, as the name indicates, is supposed to not modify the buffer. So we compute the checksum of the buffer before and after the read-only client, and then we assert that they are the same at the very end. Now, you can verify this example in separation logic, and this is what it would look like. After we produce the buffer, we get a point to the buffer contents, as let's say a list of integers u. And then we compute the checksum. And we need to remember something about check1 now to do the rest of the verification. So what you would typically do in separation logic is define a mathematical version of the checksum function. CS here, that is then applied to the buffer contents. And we just remember that check1 is CS of u. We call read-only client, and then afterwards we compute checksum a second time, and we remember that check2 is CS of u. And then we can prove that the assert succeeds because check1 is CS of u and check2 is CS of u, so they both must be the same. But there's a little bit more to the story here. If we want to verify the entire program, we also have to verify checksum. And that involves providing the code for checksum, of course. But then we also have to define this mathematical function CS that operates on the buffer contents. And then there's also proof obligation. We have to show that the code actually implements this function. Which means, in other words, we actually end up proving functional correctness of the checksum function. Now, if you think a bit about this example, then you might realize that that's a bit overkill. For this example to work, we only need that checksum behaves like a function. So it should be deterministic, it should terminate, it should modify the memory, but we don't really care about which algorithm checksum implements. In particular, there's a lot of redundancy between actually providing the code and then separately providing basically the same thing again as a mathematical function. It would be nice to avoid that. And that's where heap-dependent expression assertions come in. First of all, they are logic-level assertions, so we can use them in our specifications and we can use them in our proofs. And they're assertions about program expressions that themselves can access memory. So how does this help us in our proofs? Well, with heap-dependent expression assertions, checksum of b equals check1 is now a logic-level assertion that we can use in our proofs. So here's how the proof would change with heap-dependent expression assertions. We first get that points to for the buffer, and then instead of having this mathematical function, we just remember that checksum of b currently evaluates to check1. We call the read-only client, and afterwards we remember that checksum of b also evaluates to check2. And then the proof obligation in the end becomes that if checksum of b equals check1 and checksum of b equals check2, then check1 must be the same as check2, which is of course trivial in this case. So now, for the rest of this talk, let's turn to the second question. Can we actually usefully integrate these heap-dependent expression assertions into separation logic and into Iris in particular? And that's what we did in this work by introducing Daenerys, which brings heap-dependent expression assertions to Iris via a new form of resources, unstable resources that, as we will see in a second, violate the central frame rule in Iris, and a new modality, the frame modality, that now controls how framing works. And really, the narrows consists of two parts. The first one is how we model heap-dependent expression assertions in Iris. And for that, we have developed a version of Iris with unstable resources. And the second part is then how we reason about these heap-dependent expression assertions, and in particular, how we connect them to SMT solvers. So let's start with the first one. Why is it even hard to bring heap-dependent expression assertions to Iris? I've already hinted at this a bit earlier. They assert facts about the contents of memory without asserting the corresponding ownership. And that is not something you should do in separation logic. So what they do is they violate the central frame rule of separation logic. In particular, Iris supports this very general form of the frame rule, which says if you have proven a Hall triple PEQ, then you can frame on any additional resource R, and it will be left unchanged. And this is a, if not the key principle in separation logic to achieve modularity, and used quite widely in Iris. But in the presence of heap-dependent expression assertions, this rule as it is written here is unsound. And to illustrate that, I've brought along a counterexample. Suppose we have a buffer initially storing 5 and 7, and now we update the first entry in the buffer to store 42. Typically, with the frame rule, we could frame anything around this, including, in the presence of heap-dependent expression assertions, the fact that checksum of B currently evaluates to check. But of course, if we change the contents of the buffer, then the checksum cannot stay the same. And that is actually quite a problem, because Iris bakes in framing at its very core. It is central to how resources in Iris work. And so what we did in this work is we redesigned framing from the ground up. So we started with the resource layer of Iris and added a new form of unstable resources. For the Iris experts in the room, what's going on here is that typically every update in Iris preserves all potential frames, and we changed that. We introduce a new update that discards part of the frame, the unstable part, and only preserves the stable part. On top of that, we have then defined a new points to assertion that describes the contents of memory without asserting ownership, the unstable points to, and that is erased on updates, and a new modality, the frame modality, that now controls how framing works. On top of that, we have defined one core heap-dependent expression assertion for evaluation, namely that E currently evaluates to the value V, and we have revised the frame rule to now include the frame modality. I want to linger on that last point for just a second and explain how framing now works in the narrows. For existing resources, such as points to that carries ownership, we can just put them inside of a frame modality, which means we can arbitrarily frame them. Heap-dependent expression assertions alone cannot be framed. As we saw earlier, that would be unsound. But what we can do is, if we have a heap-dependent expression assertion, together with enough ownership to stabilize it, to make sure that its value will not change, then we can frame the two together. Now next, let me say a few words about how we connect these heap-dependent expression assertions to SMT solvers and how we reason about them. Typically, there's quite a wide gap between the Iris world and the SMT world. In Iris, we reason about separation logic, and we do so mostly manually using the ROC proof assistant. SMT solvers, on the other hand, provide great automation, in particular for theories like big vectors and integers, but they reason about first-order logic. And heap-dependent expression assertions are one nice way to bridge this gap. More specifically, they allow us to use SMT solvers to automate parts of an Iris proof. Let me explain in a little bit more detail how this works. So at the top here, I've written a formula in first-order logic. And this is something that an SMT solver could understand. It says that if for every buffer B and unsigned integers, 64-bit integers C1 and C2, if the checksum of B equals C1 and the checksum of B equals C2, then C1 must be C2. This is basically the formula that we've been working with so far. Here's it written out as a heap-dependent expression assertion again, in full detail. And the point I want to make here is that they are very similar, but, as I will show you now, they're also subtly different, and that's where the work of this part went. In first-order logic, we have uninterpreted and interpreted sorts. In heap-dependent expression assertions, on the other hand, we have separation logic predicates with unstable resources. In first-order logic, reason about things like uninterpreted functions. In heap-dependent expression assertions, that is the program code itself. That's the whole point of having the program code at the assertion level. In first-order logic, we have first-order equality, two equate terms. In heap-dependent expression assertions, we reason about evaluation. More specifically, we want to evaluate our expressions. And then lastly, in first-order logic, we have implication. This is the classical implication of first-order logic, whereas in heap-dependent expression assertions, we have the implication of separation logic. And if you know the two, you might also know that they behave quite differently. So what we did in this work to bridge this gap is we proved the following key theorem. We established a connection between heap-dependent expression assertions H and first-order formulas pi, such that if pi holds in first-order logic, then we can assume H in iris, where the connection is basically the one that I outlined on the previous slide. So for example, we would relate the code of checksum to the uninterpreted function checksum. And then the proof of this is beyond the scope of this talk. You can find the details there in the paper. But basically what we do is we construct a model of first-order logic based on heap-dependent expression assertions, where we define a logical relation that itself is a heap-dependent expression assertion to interpret first-order sorts. As I said, you can find the details of this in the paper. What you can also find in the paper is an evaluation with several case studies, including some that illustrate the strengths of heap-dependent expression assertions, some that leverage the connection to SMT, and in particular their bit vector theories, and some that go beyond what Iris and Viper can do individually. And the Iris is fully mechanized in ROC and extending Iris. And with that, I thank you for your attention, and I'm happy to take any questions that you may have.
Hi, great talk. Matthew Parkinson, Microsoft. Could you talk a bit about non-determinism and if this works for non-determinism?
Good question. So we require the expressions themselves in the heap-dependent expression assertions to be deterministic, because otherwise, for example, basically the implication that I showed you on the slide wouldn't hold. But the programming language itself doesn't have to be deterministic. That can have concurrency, as we actually do in the paper, and lots of other non-determinism if it wants. The crucial bit is that the expressions for that particular notion of evaluation that we've chosen are deterministic.
Hello, really enjoyed the talk as well. Can you talk about how the frame modality relates to the previous formalization of implicit dynamic frames?
Yes.
My understanding is, of the former, is that you just make sure that every expression in the logic is well framed. So I wonder if there's a relationship there.
Yes. So basically, I tried to write this down in a separation logic style to match the rest of the talk. But what you usually do in implicit dynamic frames is you separately, outside of the logic, assert that the proposition is self-framing, the one that you want to frame. And what we do in Daenerys, one way to think about it, is we internalize that notion into a modality that you can then have in a logic and pass around.
Thank you.
Hi, really cool work.
Thanks.
So, I mean, I'm sure you're aware there's this other work about the next-gen modality, which also introduces a feature which breaks framing and also solves it by introducing a new modality. Have you thought at all about the similarity between these, if they're, one encompasses the other, or even if they're compatible?
Yes. So the next-gen modality, as far as I understand it, basically applies a function to the resource that says, okay, this is how the resource should change. And so instances of their modality that they show are persistency and plainly, for example. We want something different in that we want to preserve the spirit of the frame-preserving update. So we want to have this implicit version where you as the user decide when you see the update what you actually want to update. which needs this, I think, frame preservation style. Right, so I think the two are quite different, although both do not preserve frames.
Thank you.
Hi, very cool work. I wanted to ask about how inconvenient the proofs are. So one of the benefits of the original iris that you can try blindly framing everything, and if it doesn't, and if you have some other research left that you start manipulating. But here I saw that depending on the situation, you might need to combine certain resources first to make it stable and then frame it. And I think that might become inconvenient as the proof gets larger.
Very good question. So for existing iris things that already basically are stable, like the points 2, you can just continue to frame things. And we actually changed the iris proof mode a bit such that it can interact with the frame modality. And so when you write iframe, it will just frame those away automatically. For heap-dependent expression assertions, indeed, there's a bit more work involved. It's kind of pay as you go. If you want to use more heap-dependent expression assertions, you also end up with more frame replications.
Right, thank you.
This is really cool. I just wanted to a remark. So Emmerich Fromhertz in his PhD thesis in the Steele logic has a notion of heap-dependent expressions that he calls selectors that are included in as part of the separation logic of Steele. One thing that he has, his selectors are required to always be self-framing, and there isn't a way to sort of split apart the sort of the permission from the heap-dependent expression, which you seem to have, which is cool. But I just thought I'd mention that.
Yes, thanks for that pointer. And it took us quite a bit to actually get the star in between those two guys.
I also have a question. So it's maybe more of an engineering or organizing question. So you said you redesigned Iris from the ground up. So did you actually manage to merge this into mainline Iris? Did you break all the existing Iris proofs? How much of the narrative is now on top of Iris? How much is merged? And kind of these practical questions.
We broke all of Iris. No. So far we've developed this as a completely separate fork. At some point, we basically didn't change the weakest precondition of Iris yet, and we changed everything underneath. And then we just ran make to see what happens, and it compiled everything. We were a bit surprised. So I think basically the model is sort of just an add-on on top of every single thing. So where Iris has a U camera, we define on top one that distinguishes stable and unstable elements. And we can turn existing resource algebras into ones with unstable elements by just saying, well, everything is stable and there's nothing unstable. So that part is backwards compatible, and I think we could upstream that. Then one would have to see whether we would want to maintain a separate weakest precondition inside of Iris, outside of Iris, that sort of thing. We also did a couple of experiments to see that when you can replay existing Iris proofs, and because everything is stable there, you just write basically imod intro a bunch of times, and then that's it.
Cool. Okay, so let's continue with the next talk. We have Sunho, who is going to tell us about relaxed memory concurrency.
Hello, I'm Sunho Park, and in this talk, I'm going to introduce our work on verifying lock-free traversals in relaxed memory separation logic. As the title suggests, our main focus is to verify lock-free traversals, and we consider lock-free versions of linked list or scheme list algorithms, and these are used to implement set or map data structure, which support operations like insertion, deletion, or membership testing of a key. And additionally, we consider priority queue data structure, whose main operation is removal of the minimal key in the current priority queue. However, proving these data structures is very, very challenging, even in the ideal memory model, which is called sequential consistency, or SC. The root cause of this problem is that we have to consider concurrent modifications to the list while traversing the list without locking. So as a result, many people are still working on this topic even nowadays. And in the last year, the first formal verification of scheme list under SC was first reported. However, to best our knowledge, no work has fully focused on a realistic memory model called relaxed memory consistency, or in short, RMC. So in this work, our main focus is to build the necessary theoretical foundation to verify these algorithms under relaxed memory consistency. And we report the first mechanized verification of them. Our main results comes in two parts, the specification and verification. And let us first begin with the specification part. In sequential consistency, linear usability has been widely used as a correctness condition of concurrent data structures. Its key idea is to linearize the concurrent execution, and on the linearization and on that total order, we understand the behavior as if we are considering a sequential object. This simple idea is widely applicable in SC, but the problem is that it cannot be extended to the more realistic scenario, which is modeled by RMC. To explain this, let us consider that we are using a modern multi-core CPU, and suppose that we are running multiple threads on different cores. In this scenario, suppose that a thread T1 removes the node 2. However, it may be the case where CPU wrote this new blue edge only to its own cache without writing to the main memory. And if it is the case, then even if a thread traverses the list after the T1's operation, it cannot read the new edge and arrive at the node 2. It results in a situation where T2 still finds the key 2 even if it is executed after T1's operation. Obviously, this is a violation of the sequential behavior of the set data structure, so it cannot be explained by the original linearizability. And moreover, this complex behavior also complicates the verification process. To explain this, I briefly explain the actual semantics of the relaxed memory consistency. Under RMC, the global memory state is the history of all written values. For example, if we store a new value to the global variable x, then the new value is simply appended to the history without overriding the previous value of 0. And whenever we read from a global memory, relaxed memory consistency allows us to read an old value recorded in the history. And in this process, we actually cannot read a very old value that violates the causality. For this, each thread under relaxed memory consistency tracks the knowledge of observation, which is the last value it read, wrote, or synchronized by memory barriers. And using this knowledge, relaxed memory consistency this allows reading or writing very old value which are older than the observed value. And with this model in mind, here's the correct view of the linked list on the relaxed memory consistency. Because the global memory state is the history of all written values, linked list structure should be viewed as a directed acyclic graph that contains all the stale edges on the memory. Even more, we have to reason about thread-dependent reachability. For example, we need to prove that this purple edge cannot be traversed by some threads who have observed insertion of the very new node V6. These two parts are very unique but inevitable in relaxed memory consistency, and these become the major challenge in verification. So in our work, we solved the two challenges, and for the specification challenge, we introduced the method of per-key linearization, and for verification challenge, we developed a shadow violation to reason about thread-dependent reachability. Let us first talk about the specification. Our per-key specification is based on a variant of linearizability for relaxed memory consistency, and it is called linearizable history specification. I briefly explain its main idea by using our previous example. As we previously discussed, this scenario cannot be explained in the original linearizability under SC because contingent operation of the T2 must fail after the remove operation by T1 based on the sequential behavior of the set data structure. And linearizable history specification fixes this problem by additionally allowing that unsynchronized events can be freely reordered even if their execution times do not overlap with each other. So in this example, we can freely reorder the two operations between T1 and T2, and we can consider this new linearization order. And we can easily check that this linearization order now satisfies the sequential behavior of the set data structure. And in fact, this idea is widely applicable to relatively small data structures like stacks or queues. But the problem is that this idea cannot be applied to more concurrent and complex data structures, especially the set or map data structures we consider. The root cause of this problem is that these complex data structures only have very weak guarantee, and which does not allow to consider this kind of total order at all. And here's a simple counterexample for that. Consider a scenario where T1 and T2 insert the two keys, and then they traverse the list again to find the another keys, 3 and 1. In this scenario, what's unique in elect memory is that both traversals can fail to find the keys simultaneously. This is not appear in the sequential consistency, but this is allowed in elect memory consistency. And if it happens, we can easily check that no linearization order satisfies the sequential behavior. So this cannot be explained by the linearizable history specification. And we have to find a solution to explain this scenario. Actually, what we can learn from this example is that operations on different keys are basically independent of each other. So this means that addition of key 1 has nothing to do with traversal for finding key 3, and addition of key 3 has nothing to do with traversal to find the key 1. And based on this observation, our fix to the previous linearizable history specification is that we are now considering multiple per-key linearization orders instead of a single linearization order for the data structure. Here, each per-key linearization order consists only of the operations on that specific key. And we actually found that this simple idea has very widely applicable to all our case studies, including the very complex one, the priority queue example. Furthermore, this idea retains the high, strong power in client reasoning, and we checked it by lots of various client examples. This concludes the explanation to our new specification, and now let's focus on the next topic, which is the verification of the thread-dependent reachability. To explain with an example, let's consider the prior example, and additionally suppose that T1 traverses the list after removing the key 2. Intuitively, this traversal to find the key 2 must fail because that key was previously removed by itself. And actually, this is also what is guaranteed by our specification. So we have to consider this kind of causal reasoning in actual verification. On the semantics level, we can verify this property by using the coherence of elect memory consistency. To elaborate, we can prove that T1 cannot traverse to the node 2 because the coherence of the elect memory does not allow reading an old purple edge after writing a new blue edge. At the essence of this reasoning is a causal order between the two edges, where old edges become unreachable by observing new edges. And one of the main contributions of our work is to formalize this kind of causal relation. And for this, we devised a new relation called shadow-by relation. Shadow-by relation is a relation between two edges on the global memory. And E1 shadowed by E2 means E1 is strictly earlier than E2 in a causal order. So in other words, E1 gets unreachable after observing E2. This is the main intuition behind shadow-by relation. And this relation can be easily established during the insertion or deletion of each data structure operation. And furthermore, this relation is transitive. And this transitivity is used to establish the causal order between two edges far away from each other. For example, suppose that current thread has observed this purple edge. Then by applying the previous proof rules, we can derive that these shadow violations. And now by applying the transitivity, we can prove that this thread cannot traverse to all the stale edges. And in general, this transitivity reasoning can be used to derive the set of all stale edges that cannot be observed by, that is unreachable by each thread. And this is the essence of causal reasoning in actual verification. And the actual model of shadow violation is based on the coherence of elect memory. Formally speaking, E1 shadowed by E2 means for every traversal to E1, it intersects with what we call reference path to E2. And among the intersection points, we can always find an incoherent step. And due to this existence of the incoherent step, it implies that every traversal to E1 is not possible for some threads who have observed E2. This matches with the intuition behind the shadow violation. Here, the reference path is defined in a way that observing E2 implies observation of the entire path. So we can use the coherence reasoning in this definition. And in fact, the reference path is defined in a way defined as the path with all its incoming edges to all its internal nodes. Although I'm not going to explain more about this topic, I briefly mentioned that this precise definition of reference path plays a very important role in establishing the transitivity of the shadow violation. And finally, I briefly explain how this shadow violation is actually used to verify our per-key specification. I'll explain with a simple example. Consider a scenario where T1 removes the key 2, T2 finds the key 2 by taking the stale path, and T1 does not find the key, and T2 adds a new key. And in this scenario, observe that these highlighted edges can be sorted by the shadow by order. So in this situation, our main strategy of deriving the linearization order of these 4 events is based on the shadow by order, as shown in the screen. The main benefit of this strategy is that we can immediately apply the shadow violation to show that this linearization order does not violate causality. So it's only left for us to show that this order satisfies the sequential behavior of the data structure, and we found that it can be done without any major difficulties. So to conclude, we present the first formal verification of log-free traversals in Lex memory separation logic. And while doing so, we devised a new specification called per-key linearizable history specification, and we devised a new shadow violation to reason about thread-dependent reachability. And in our paper, more details about specification of complex operations or reason behind the particular choice of the reference path can be found. Thank you for listening, and I'm now happy to answer any questions.
I have a question to get started. So, good specifications are two-sided. That means both the person who implements the specification finds it easy to use, as well as clients. So you told us about how to verify data structures, so you're on the implementer side, but did you also try out if a client of this data structure could use it conveniently? So that's part 1 of the question. And then part 2 of my question is, would weak memory artifacts still show up in the specification of a client, or would you be able to hide the weak memory stuff and have a very pretty and simple specification of the client?
Okay, thank you for great question. For first question, we have actually done lots of very in-depth evaluation of the client reasoning, and actually there will be a talk about verifying RCU algorithms on the elect memory. And in that project, we employed our per key specification as a small as a specification of the internal module of the RCU algorithm, and we used that specification to verify the entire RCU algorithm. And details will be given in tomorrow's talk, or details can be found in the paper. So for short, we have evaluated the client reasoning, and actually it is quite convenient. I would say it is convenient to conduct client reasoning compared to some other possible specifications that we have ever proposed. And for the second question, can you reply the separate? Yeah.
Yeah. So the second part is I'm not very good at weak memory reasoning. So if I read the specification of your client, can you write it without any weak memory artifacts and just a very simple functional correctness?
Okay. Thank you. And for that part, you can actually you can either choose to hide all the elect memory effect, but in that case, you cannot get very very specific. The specification loses its power. So a client cannot reason some very trivial programs without that specification. And our specification contains the bare minimum for the for strong client reasoning. And we tried our best to make it very simpler, but retaining its strong power. So that's our main point of the specification. Thank you.
Do we have other questions from the audience? It looks so, yeah.
Hi, Matthew Parkinson, Microsoft. Thanks for the talk. I was wondering if you had anything about how the memory model you're considering here relates to like the memory models in languages or like at the hardware level, kind of, because you had a very abstract view of sort of weak memory here.
Yeah, actually our work is based on the C++ elect memory model. So we are already considering the language level elect memory semantics. And as long as I know, this language level semantics already captures many parts of the all hardware level elect memory semantics. And I believe this C or C++ memory model, especially we are using the operational version of RC11 memory model. It has already incorporates all the hardware details, and yeah, I think it is already strong enough to consider many kinds of elect behaviors occurring in the either language level and hardware level.
Hi, I'm Dongjia Li from MIT. Thank you for the great talk. I have a question about synchronizations. So if I know correctly, weak memory has some synchronization mechanisms, and I can imagine that it will interact in some interesting ways with your new specifications and also your verification techniques. And I think I have some question about how they do interact.
Can you elaborate more on how the interaction part, interact with the client part?
So weak memory fences would show up in this history of executions, and that will, I guess, have some effect on linearizability spec.
Okay.
And,
yeah, I got, elect memory consistency, the RC11 memory model also has the different kinds of synchronization, which includes using some fences or some least equal synchronization by atomic excesses. And our model, our verification method and the specification does not rely on that part, because reasoning of this kind of internal synchronization is actually done by the previous work that formalized the separation logic for the elect memory consistency model. So you can just use the existing proof rules to reason about the synchronization. And yeah, these reasoning principles align well with the previous the IRC 11 separation logics predicates or proof rules. So I don't see any difficulties when reasoning about the synchronization in various methods. Yep.
Okay, so it's time for lunch. If you have more questions, you can ask him later. And let's thank the speaker again.
Hello, everybody, and welcome to the second session of the second day of PLDI. I hope you're having a good time, and I hope you had a good lunch. So this session is, so it's labeled automata theory, although I would sort of call it a mix of automata theory, logic, type theory. And our first talk in this session is by André Lengal, and he's going to talk about how to handle position constraints in modern string solving. André.
Okay, thank you for the introduction. Thank you everybody for coming to this talk. This is a collaboration with people from Brno and also ufunction from Academia Sinica in Taiwan. So what are we talking about here are string constraints. String constraints are constraints in this SMT theory of strings. So you have a first order logic that is treating the string as some basic data type. And the constraints look similarly to what is written in this slide. So you can have some equations, you can have some disequalities, these can be of some variables, or it can be of concatenations of variables, potentially with some constants inside. You can have some regular constraints, so you want to say that some variable belongs to some regular language. You can have length constraints, so you can say the length of some concatenation of variables is 3 times smaller than something else. Or you can have also some more expressive constraints, such as not contains something. Why is this important? It's important because if you want to reason about programs that are dealing with strings, and these are currently many programs because string is the basic data type of a lot of scripting programming languages, you can use this logic to express things like some SQL injection attacks in PHP or things like that. Or it can also be used in analysis of some access policies, such as they use in AWS or in Rego. Recently, it has started to be widely implemented in solvers, both in some deduction-based solvers, such as Z3 or CVC5, as you probably all know. And also, there is a bunch of so-called automata-based solvers like Norn, Trauslov, Ostrich, and Z3 Noodler. Z3 Noodler is a solver that I'm a member of the team developing it, and this is a very interesting project because we started something like 2 years ago from nothing. We started building on top of Z3, removing the basic string solving algorithm, exchanging it for automata-based solving algorithm, and we got to the place that in last year in SMT.com we won the string category in all of the possible scoring criteria. In this talk, I will be talking about just some fragment of string constraints. I will not be talking about word equations. These are solved by some other works. I will be talking about constraints which are, in particular, regular constraints. So we consider that the string variables are all have some regular language that they belong to. And then we will be talking about disequalities, length constraints, symbol is at a position or symbol is not at a position, not prefix, not suffix, and not contains. These things will be called position constraints. Why will they be called position constraints? The reason is that they are satisfied by an existence of an interesting position somewhere. So if you look at this example of some disequality, xaz is not equal to ux, this is satisfied if there is some natural number I such that if I look at the index I in this concatenation, it is not equal to this index, to the position at the index in the other concatenation. So if you look at it in this picture, there is some kind of mismatch between the occurrence of at some position in Z and some position in U. For not suffix of, I can also express this as some kind of existence of an interesting position, in this case from the back of the strings. And if I look at not contains, this is more complicated. I will be talking about why it's complicated later. Now we have some kind of like, if there is some not contains, I'm saying that for all offsets, there is some mismatch somewhere. So I have something like universal existentially quantified formula. Our approach is how to solve these constraints is that we will construct a special kind of an automaton called a tag automaton. This is nothing fancy, it's just a finite automaton that is extended in some simple way. I will talk about it later. We will use some very nice theorem that you have all learned in the kindergarten, so-called Parik's theorem. For this talk, we will use a very simplified version, which is saying that the number of occurrences of symbols in words in regular languages can be described by a linear integer arithmetic formula. So if you have regular language and you are only interested in the number of occurrences of symbols in the words which are generated by this language, then you can use a linear integer arithmetic formula to encode it. And then we will construct a Parik formula which will be encoding these constraints into a linear integer arithmetic formula, and then we will solve it by the off-the-shelf linear integer arithmetic solver. So what are these tag automata that I will be talking about here today? So the tag automata are over some set of tags, which is just some set of some things. And it is an extension of finite automata, where the only difference is that on the edges of the automaton, there is not a single symbol, but there can be multiple symbols. So you can see it as you have a word, and at one position of the word, there are multiple overlapping symbols, and all of them are somehow active at the same time. So there is an example of some tag automaton. This looks very similar to a finite automaton, and we will be constructing this tag automata from finite automata just by taking the finite automata and putting there some special tags. In this case, we take two automata, automaton for the language of a variable x, automaton for the language of variable y. We are connecting them together. By this dashed line, I'm expressing something like an epsilon transition, which is just encoded as a transition where the set of text is empty. And with this automaton, we will construct their Parik formula. So as I said previously, we will construct a linear integer arithmetic formula over variables which are taken from the set of tags, and we get for every tag in the set of tags, we get a new variable which will be encoding the number of occurrences of the tag in the accepting run of the tag automaton. So assignments are corresponding to mapping of the numbers of tags to some natural numbers. And if we have some assignments, so it is a model if there is an accepting run in the automaton such that the image of this assignment or the assignment to this variable is the number of occurrences of a tag in a word which is accepted by the automaton. So for example, if I have this word AB, AC, AC, so it is in the language of the automaton. If it is in the language of the automaton, then this assignment, so if I assign number 4 to the number of occurrences of the tag SA, number 2 to the number of occurrences of the tag SB, and 2 to the number of occurrences SC, should be a model of the Parik formula of the automaton. So let's start with the basic, with the simplest constraints, which are length constraints. An example is here. So this is an example of a length constraint. These are regular constraints, so they are implicit in everything we are talking about. And we have some additional thing here, which is talking about the length of the strings. So what do is we construct a tag automaton by connecting the automata for the variable x and y. So this is the automaton for the variable x. This is the automaton for the variable y. We transform it into tag automata. So we change the standard symbols into the set of tags, and for each standard symbol, we just put there this tag SA, for example, SB, and so on. And for every variable, in every transition in the automaton for the variable, we put there a tag LX. So if we count the number of occurrences of the tag LX in the automaton or in the formula or in the Parik image of the formula, we will know what is the length of the length of the word which was generated here. So example of how to translate this constraint into the linear integer arithmetic constraint is that we take the Parik formula of the automaton. I will not talk here about how to construct the Parik formula. That is a thing which is somehow standard in the literature. And we put there additional constraint, which is saying that 2 times the number of occurrences of this tag needs to be equal to 3 times the number of occurrences of this tag plus 2. Okay, now let's come to a single simple disequality. So I will be talking about disequalities because they are the basic things we are dealing with here. And we have a simple disequality where we have a single string variable on each side of the disequality. So what will we do is that we will construct a tag automaton where the tags are now more complicated. So before we had these tags where we were having the symbols and we were having the lengths. Now we will also put there another tags, the position tags, px, py, and mismatch tags. And the idea of what we will do is that we will construct the tag automaton as in the case for the length constraints. If I come here, so we will construct this thing, and we will make several copies. We will make 3 copies that will encode how many mismatches we have seen. Because what we need to do is that we need to guess some position in X where there is a mismatch, and we need to guess a position in Y where there is a mismatch. So we need to have these 3 copies of the automata in order to be able to say whether there was a mismatch and at which position it was. So in the first copy, we know that there needs to be some mismatch in X, so we will pretty much start accepting something here. We will non-deterministically move to the second copy after guessing some mismatch in X. Here in the second copy, we need to make a transition from the automaton for X to the automaton for Y. And then at some point, we need to again make a non-deterministic transition to the third copy, where we know that we have already seen all the mismatches. And what we are doing along the way is that we are counting the number of P tags, the position tags. So you can see there are some PX tags in this part in the first copy. There are PY tags in the second copy. So we are counting the number of position tags, and we need to say that they are the same. So if I look at the final constructed automata, it needs to hold for the constraint to be satisfied that these numbers are the same, and also it needs to hold that there is really a mismatch. We need to check that the disequality really holds, so there is some position such that the symbols are not equal. So we need to check that the number of occurrences of this mismatch with some symbol A is different. It's less than 2, so that we cannot have like the mismatch cannot be over the same symbol. If we look at something more complicated, which is having a single disequality, which is not simple anymore. So in this case, we have on the both sides of the disequality, we have not a single variable anymore, but a concatenation of several variables. So this is a more complicated because now the mismatch can happen in several possible cases. So the first case is it can be between X and Y in this part. It can be between X and X. It can be between Y and X in this part, and also it can be between Y and Y. So now we need to extend our set of tags by having possible mismatch positions in X for the first mismatch and also in X for the second mismatch, and the same thing for Y. And we also need to extend the tags for the mismatches. And then the automaton looks a little bit more complicated. On the left side, these are 3 copies of the automaton for the variable X. In the right side, there are 3 copies of the automaton for Y. And we are also need to, the runs here pretty much, the accepting runs which go from the initial state, which is here, to the final state, which is here, need to see 2 mismatches. And they can be even in the same variable. So if I look at some particular position of the mismatch, let's say if it's in Y and it's in Y, the both mismatches are in Y, then there needs to be a run that does something in this part here, then jumps to Y, sees some mismatch here, sees some mismatch here, and so on. And this can be again encoded by a linear integer arithmetic formula that we put in conjunction to the Parikh formula. This is only for one case, but we can encode the other cases in a similar manner. For multiple disequalities, this is harder, so I will not go into details. The naive solution is combinatorial, so something bad, but it can be solved in a simpler way with a linear number of, with linearly increasing the size of the formula. If you want to see details, please go and check it in the paper. For other constraints, for not prefix, not suffix, and add constraints, this is a very similar technique, so you can just pretty much extend it straightforwardly. Not contains is more complicated. So in not contains, there is some implicit universal quantification that I talked about before. Because if you want to say that that some string is not contained in another string, you need to consider all possible offsets from the beginning. You could be tempted to solve it by some kind of universally quantified formula, but the problem here is that the universal quantification doesn't work. The problem is that after the universal quantification, there is some existential quantification over the transitions. So you would have the same number of occurrences of symbols, but they could be somewhere else. So you would be considering different words. So it doesn't work anymore. There is some example. If I have these two automata for U and V, then I can. If I have these possible models A, B, A, so this would not be a model because if I shift U1 to the right, then this is contained in V. But if I rearrange the symbols, then it is not contained as it is shown in this example. So we can only solve not contains for a restriction to something which is called flat regular constraint, which are constraints that disallow this kind of looping. So you can still have loops, but you cannot have multiple loops that come back into the same state in the automaton that is encoding the regular language. The details are in the paper. For the decidability and complexity, so if we take the basic regular language constraints and put their single disequality, this is decidable in polynomial time. If we take multiple disequalities or some combination of not prefix, not suffix of, this is NP complete. If we put there not contains over flat regular constraint, we get to non-deterministic exponential time. This is because we start having universally quantified linear integer arithmetic formula. And if we start with, if we also put there word equations, which are chain free, which is some very interesting fragment for which many things are decidable, we still get a decidable fragment where the decidability is in, it's in elementary, but it is not a lower bound. For experimental evaluation, we try to compare with the state of the art, which is CVC5, Z3, and ostrich on benchmarks from symbolic execution and of some handcrafted formulae. The results are, so we were mainly trying to improve over the original performance of Z3 Noodler, which if you look at the last column, it helped a lot. These formulae were not cherry-picked, so there are most of the formulae are easy to solve. So it seems like we might have improved by solving like maybe 1% more of the benchmarks than previously, but this is from all formulae. Many of them are very simple. What is interesting is comparison with the state of the art, which is Z3 and CVC5, and this shows that our approach is orthogonal, so it is a very good match for a portfolio solver, and it can be beneficial to use this in some kind of application where you can have to have portfolio. Okay, so to conclude, I was showing this way how to deal with regular constraint by translation into tag automaton and linear integer arithmetic solver. It is efficient in practice, so that's nice. And in future, we want to solve the not contains, which is non-flat. We have some result now, which is under review for one not contains, and we want to go for some richer regular constraint that can have some back references or bounded repetition. Okay, thank you.
All right, do we have questions? Okay, so can you also tell us about what constraints you probably cannot solve using tag automaton?
Okay, so what we cannot do is word equations, but they are solved by something else. They are solved by some other techniques. There is if you take word equations which are unrestricted and length constraints, the decidability is not known. And what we don't consider yet are some things like transducers and stuff like that. So I think that many of them could be solved. In general, it is undecidable, but maybe there are some decidable fragments which might be.
So when you have length constraints on top of word equations, don't they translate to position constraints?
No. No, the thing is that because for word equations, if for a vertical equation to hold, that means that all of the positions need to be the same. While for the position constraints, it's enough that one position is different. So it's like
so if I have upper bounds on lengths, then I can write it.
Yeah, if you have upper bound on length, that's all. Yeah.
Okay. All right. Let's thank Andre again. Next, we have Steven Schaefer from Michigan, and he's going to talk about how to reason about parsers and grammar theory in dependent Lambert calculus.
Yes, hello. So I'm Steven, and this is work from me and my collaborators Nathan, Pedro, and my advisor Max, who's here if you guys want to chat afterwards. So parsing is one of the oldest and most studied problems in computer science. And in its simplest form, I mean, a parser is going to take some unstructured text and maybe turn it into a structured representation like a syntax tree. And I'm sure we're all familiar with parsers. Despite what people might frequently say, parsing is not a solved problem, and the cost of insecure parsers can be quite severe. So for instance, many critical real-world vulnerabilities arise as parsing vulnerabilities, including the Equifax hack from 2017, which leaked the financial data of 150 million Americans, probably like a third of the Americans in this room. And for the people here at PLDI, verified parsing is also important because unverified parsers can jeopardize the guarantees of otherwise verified software. So for instance, early versions of the CompCert verified compiler didn't have a verified front end, and the C-Smith bug finding project found 0 middle or back end bugs, but it found 6 parsing bugs, meaning a user of CompCert as an end-to-end system has a slightly weakened correctness theorem that they can leverage from this as a verified compiler. So to verify a parser, we got to give a specification for what a verified parser is. And for me, a parser for a formal grammar A is a partial function that takes in strings, or sends strings to parse trees of that formal grammar A and might fail, so it is a partial function. And when we verify these parsers, we want to verify 2 key properties. One, we want to verify that the parser is sound, meaning for some input string W, when the parser claims to have returned a parse tree f of w, it's a valid parse tree for the proper input, or for the proper formal grammar A, but it better ought to be a valid parse tree for the same input string w, so the parser doesn't change the resources being parsed. Further, we want to verify that a parser is complete, meaning that a parser returns a parse tree whenever one does indeed exist and doesn't prematurely or incorrectly fail. And so with this specification of what a correct parser is, we can take a look at some of the existing verified parsing works. And existing verified parsing implementations often laser in on a single formalism or a single algorithm, such as LVAL parsing, LVAR, or one of these many others. And these are great works, but they miss a key opportunity to reuse some shared kernel of grammatical foundation between projects, because each of these formalisms necessitates its own verified implementation, and they're often duplicating work by what they mean by parser, what they mean by formal grammar. And so verification of parsers could be made easier if all of these systems could be laid on top of a single foundation. And so in this work, we present dependent Lambert calculus as a unifying formalism to describe intrinsically verified parsing. So dependent Lambert calculus, or lambda-d, is a functional programming language for writing verified parsers, and it's built atop an ordered and linear type system such that parsers written in lambda-d are sound by construction. And through a little bit of effort, we can further guarantee that parsers in lambda-d are complete. And in total, this is an extensible system for describing several grammar formalisms, their parsers, and even their parser generators. And like I said, it's a linear ordered type system. The way that lambda-d is going to encode these existing grammar formalisms is by describing them each as linear types in lambda-d. And so I said the word ordered and linear as shorthand for this talk. I'm just going to call these linear types, but I guess precisely I mean ordered and linear here. And We've implemented this in Cubicle Agda as an embedded domain-specific language, and in that embedded DSL, we've instantiated verified parsers for some selected demonstrative context-free grammars, as well as written a verified parser generator for regular expressions. So throughout the rest of this talk, I'm going to show you the structure of lambda-d and the types and terms, and I'm going to walk you through an extended example of constructing a verified parser for a particular context-free grammar. So to begin, let's look at the basis for lambda-d, for dependent lambda calculus, ordinary lambda calculus. This is a logical system going back to the 60s for describing parsing deductively as the act of constructing a proof tree in lambda calculus. And so if we want to parse a string, say AB, we can decompose the resources being parsed and construct smaller proof trees corresponding to the decomposed string. And what I want to say is that in existing implementations of lambda calculus, users often don't write the program to build this parse tree or even build this parse tree manually. Rather, they provide a type level specification for what a parser, like input-output pairs of a parser will be. For instance, a user often will specify the string and the target formal grammar, and then this parse tree is not written by the user, but it's synthesized through a search procedure or through a logic programming engine. And what we've done in lambda-d, in dependent lambda calculus, is extend the expressivity of the lambda calculus by adding dependent types and providing a functional term language for which users can write programs to make these parse trees themselves. So let's take a look at some of the types in dependent lambda calculus. First, I'll show you a family of types that will correspond to the regular expressions. We can have types corresponding to characters drawn from some fixed alphabet, a type corresponding to the empty string, and then we can combine these inductively via concatenation, disjunction, conjunction, and cleany star. And so these types represent these formal grammars. But if we take a look at what we mean by cleany star here and think for a moment, cleany star is just an inductive type of lists, but linear lists combined through iterated concatenation. And if we generalize from just this particular inductive type to arbitrary inductive types over these family of base types, we can capture not just the regular grammars of the regular expressions, but context-free grammars and beyond. And in lambda-d, which I'll talk about a bit later, we can encode even grammars of unrestricted complexity. So let's take a look at how we can then use these types to encode common grammatical concepts. So I've been mentioning this as a linear and ordered system, and I guess I want to show you why. Excuse me. So first, first we're going to use terms in lambda-d to describe parse trees of strings, and in this case, the string cat. So a parse tree of the word cat will correspond to a term built in a context corresponding to the word cat. Here we just decompose the constituent characters, give a parse tree of the characters C, A, and T, and then we can combine them with the following term to spell cat. And if we want to maintain the interpretation that parse trees of strings correspond to terms built in a context corresponding to that string, we have to restrict the types of terms we can write in lambda-d to preserve that interpretation. For instance, lambda-d is ordered and has no exchange rule because while reading a string, I don't get to permute the characters. I have to parse them in the order they're handed to me, so CAT doesn't spell act. Similarly, we have no weakening rule because you have to read all the characters in a string. You're not allowed to drop any. And we have no contraction rule because you don't get to read the character T twice, for instance. And it's precisely these restrictions that ensure derivations in lambda-d are sound by construction because all the fundamental building blocks in this language necessarily preserve the grammatical content of the resources of the strings being parsed. So this is one way we can use the terms in lambda-d to describe parse trees of particular strings. We can also use terms in lambda-d to describe reductions between grammars. So let's start with a pretty simple observation. All strings parsed by the grammar A concatenated with A star are also parsed by A star. And this can be witnessed through a very simple flattening function, which in lambda-d is 2 lines of code. It really is maybe an extra line because of spacing. And so this flattening function is taking in a parse tree of type A concatenated with A star, which is just a list of tuples, and is flattening it to a single list. But because this type checks in this linear ordered system, this is carrying the data of being a reduction from parses of the input grammar to parses of the output grammar, while still being a very simple functional program that's quite easy to write. Okay, so with these types and terms in mind, I'm going to walk you through the construction of a verified parser for the Deek grammar of balanced parentheses. So the Deek grammar of balanced parentheses is a context-free grammar that's quite often written in the syntax of generative grammars as having two productions, one corresponding to the empty string and one that builds up parses of the Deek grammar from smaller parses. And similar to the Cleany star case, if you squint your eyes, this is just an inductive type with two constructors, one for each production. The nil constructor says that the empty string is balanced, and the val constructor corresponds to the second production. And just as we parse the word cat, we can parse strings into this grammar by building terms out of a context corresponding to that string. In this case, an open paren followed by a closed paren repeated twice can be parsed into the Deek grammar by building the following term by invoking these constructors in the following order to build this parse string. So with this formal grammar as an inductive linear type on the mbecd, we're now going to build a parser for this formal grammar. And let me reiterate what I mean by parser. A parser is going to be a partial function from strings to parses of the Deek grammar, and we'll represent that in lambecd as a function that takes in an arbitrary string and maps into the maybe monad acting on the Deek grammar, so either returning parse of the Deek grammar or top, where top corresponds to failure of a parser. And we can write functions with this type signature in lambecd, and their soundness is guaranteed for free by the ordered linear type system, but the completeness of a parser with this type signature is not guaranteed. For instance, we can always choose to fail, and that would be a very incomplete parser. So if we refine our notion of what we mean by like parser, we can also guarantee completeness in lambecd quite simply. So I'll say instead of a parser being a function from string to Deek or top, a complete parser for the Deek grammar is a choice of a complement grammar, suggestively named Deek complement, and a function from string to Deek or Deek complement, where we've reduced the completeness proof to the statement that Deek and Deek complement are disjoint, meaning that their intersection is empty. And so to build one of these, to build a complete parser for the Deek grammar, I'm going to use an automaton and encode an automata formalism within lambecd. So taking a look at the following machine, this will serve as the parser for our grammar, and this machine has a state for each natural number, and will increment the state every time we see an open paren, decrement every time we see a closed paren. We want to capture the structure of this machine within lambecd by encoding it as a linear type, and the linear type that we're going to use is this inductive linear type of traces indexed by two pieces of data, where we'll tag it with a Boolean, marking if that trace is accepting or rejecting, and a natural number that marks what state that trace begins at. And each of the constructors of this inductive linear type correspond to small modular ways we can build traces. For instance, if we want to terminate a trace in the initial state 0, because that state's accepting, we can use the first constructor. If we want to terminate a trace in the non-zero states, which are rejecting, we use the second constructor. And then the push, pop, and unexpected constructors correspond to different families of transitions. For instance, push corresponds to the open parens, pop corresponds to the closed parens, and the unexpected constructor corresponds to a failing case where we try to read a closed paren while in the initial state 0. So we have captured the structure of this machine as an inductive linear type in lambecd, and we can now build a parser for it. So here's the code that implements the parser for those types of traces. And again, it's a small, ordinary functional program, quite simple and short to write. But because this type checks in lambecd, this carries the data of being a sound and complete parser, and it's complete because the type of accepting traces is disjoint from the type of rejecting traces. And then we can use this code to build a parser for the Deek grammar as follows. So the code from the previous slide defines an equivalence between a type of strings and a disjunction between accepting and rejecting traces starting at the initial state. We can separately prove that the Deek grammar is equivalent to the type of accepting traces. So this is automaton is indeed a parser for the grammar we wanted it to be. And then we combine these equivalences to build a function from the type of strings to a disjunction between the Deek grammar and the rejecting traces out of the initial state. And this is precisely the specification for a complete parser we started out with. So to recap what we've done in this example, we've described a reusable framework for verifying a parser for a formal grammar by describing that formal grammar as a linear type in lambecd, by describing a corresponding automata formalism also as a linear type in lambecd, proving those two equivalent in the equational theory of the system, and then using that equivalence to instantiate a parser for that formal grammar. So we've done this for the Deek grammar that you've seen here, but we've also done this for an LL1 grammar of arithmetic expressions and a look-ahead automaton. And we've also done this for a verified parser generator for regular expressions, abstracting over the regular expression, generating the corresponding finite automaton, and reasoning about that equivalence again in lambda-d. And so just to reiterate what's happened here, we've taken two grammar formalisms that are a priori on different formal footing, automata and the corresponding context-free grammar, and we were able to reason about that equivalence in the equational theory of our system. And so there's a bunch of great stuff that I've elided from this talk that you can find in the paper. We're able to also encode other common grammatical notions within the equational theory of lambda-d. For instance, you can prove the unambiguity of grammars within the equational system, and that there's a distinction between this notion of equivalence I keep mentioning, where you can distinguish between grammars being equivalent when they have the same language semantics, when they recognize the same sets of strings, or if they have the isomorphic types of parse trees, and there's more information about this in the paper. I've elided much of our usage of the dependent part of dependent lambda calculus here. So we use linear, nonlinear dependent types as a sort of indexed conjunction and an indexed disjunction that I implicitly used when I said we have a type of traces indexed by a Boolean and a natural number. And these are key to describing grammars of unrestricted complexity. And lastly, I've elided much of the denotational semantics of lambda-d, which interprets grammars in the category functions from strings to sets. And this is the basis for our Ogda implementation, so you can check the paper or the artifact if you want to know more about that. Moving forward, we're looking to encode broader classes of grammar formalisms and verified parsers as programs in lambda-d, such as LL or LR parser generators or forms of context sensitivity. Looking to encode verified semantic actions and plugging them to verified language backends. Everything I've mentioned thus far has been concrete syntax, but we often want to use abstract syntax. And we believe in a modified variant of our semantics. Instead of having grammars over strings, but potentially type systems over tree-structured data, you could use a similar method to implement verified type checkers rather than just verified parsers. So just to reiterate, lambda-d is a functional programming language for building verified parsers, and we use the type system to carry a lot of proofs of correctness about our parsers. Thank you for listening.
Hi, my name is Mark Muller. I'm at Cornell. Great talk, thank you. I was wondering if the completeness guarantee requires the grammar to be deterministic context free.
I think no, and that you only need this distraightness constraint. Yeah, there's no necessity of being deterministic or unambiguous or anything like that to guarantee completeness.
Okay, I was just interested by the use of the complement and that deterministic context-free languages are closer in complement, but arbitrary context-free grammars aren't. So that's what I was worried about.
Thank you.
Thanks for a very great talk. I'm Yuda Urabe from Science Tokyo. And I would like to ask why you choose denotational semantics to why did you consider denotational semantics? Is it easier to implement denotational semantics in Ogda than operational semantics? Or
so you're asking why we use denotational semantics as like our strategy here?
Yeah.
I'd say it makes precise what we mean by the formal grammar semantics, and I guess this is my first project, so it's a notion of like what's easier if we were to do this operational or not, I don't have a necessarily a good read on, but it at least makes precise what we meant by the formal grammar semantics, and sort of, for me, I value that precision, but maybe we could talk afterwards about some of the trade-offs. Yeah.
Okay, thank you.
Hi, I'm Sarah. Thank you so much for the great talk. And I'm from University of Michigan as well. So you mentioned like you were able to like prove ambiguity, but is it like enough to have linear and ordered typing constraints to do that, or did you also added anything to like deal with the ambiguity?
I have to think about that. Can we talk afterwards about that?
Definitely.
Sorry. Yeah.
Questions? So I have a question. Using Lambert calculus, can you prove meta theorems like the closure, the intersection of two regular languages is regular, or homomorphic image of a context-free language is context-free, that sort of thing?
This is a great question. I would expect yes, but I don't know how complex that construction might get. But in principle, you could capture the class of regular grammars and then map between them as terms in the ambiguity and hopefully prove this closure procedure. But that might take a lot of manual work that I think is lost on me in this moment at least.
Thank you. Okay, let's thank the speaker again.
I don't know how to take this off.
Okay, so next up we have Charlie Murphy, who's going to talk about semantic-guided synthesis and how to verify solutions for these problems.
Hello, thank you. So yeah, today I'm going to be talking about our paper. This is joint work done with collaborators at University of Wisconsin-Madison and UC San Diego, and this is work that I did before joining Amazon. So this work is sort of inspired by the desire to do language-agnostic program synthesis. And so let's go over a few examples of what we mean by synthesis and sort of the setup that we're trying to work with. So you might try to synthesize a term from this language, and implicitly, when you're doing this synthesis, you're sort of synthesizing things against a known semantics for SIGUS or SMT terms, and with a given specification. For example, this prose that says we want to try to compute the maximum value of two variables, x and y. And so other domains, such as imperative languages, you've got this search space here that says I've got imperative, I've got a looping program that does some sort of increments and decrements on the variables x and y. And again, the semantics is sort of implicitly as an imperative or C-like language. And the specification of your program might be you're looking for a program that doubles x and stores it in y. A different domain might be that you're trying to synthesize a regular expression. Again, there might be many different kinds of semantics for it, such as the matrix-based semantics. You don't have to worry about what that is. And then your specification might be saying that I want to accept all strings that begin with 1 and end with 0. And finally, we might try to do something like synthesize an SQL query with the standard semantics of SQL. And the specification that says just return all rows within some given table when a column of that table is positive. So as a user of synthesis, what might be really complex and really hard to use synthesis tools is that when you actually try to do synthesis, there's different tools for different languages, and they each have their own input description, and the tools aren't very usable. And so what you would like is sort of a single interface for actually writing your synthesis problems. And so this is what's accomplished by the Semantics-guided synthesis framework, which requires that you provide a syntax, semantics, and specification. And so the SymGIS framework, has these three components. Going back to the first example, it's got a search space, a grammar defining the search space of programs. You have to provide a formal semantics for every element in your syntax. And so this actually looks like something that's inductively defined over your grammar. And so here this says that variable x is just returns the value of x. Variable y similarly returns the value of y. And then the value of E1 plus E2 is inductively defined by the value of E1 and the value of E2 and just summing them. You can do that for all the other elements in the grammar, but I'm not going to bore you with all that. And then if you have a specification, it's defined as a logical formula that's defined over the semantics of the program that you're looking to search for, in this case max. And this just gives a specification that says max is the thing that you, this here says that the program that we're looking for max returns some value r, and that value is greater than both x and y and equal to one of them, sort of the standard definition of max. So now that we've got this, we've defined a SymGIS framework, a SymGIS problem, and we can provide that to a tool, and we're ready to start trying to define a synthesizer that takes as one of these inputs. And for now, I'm just going to assume that we're trying to build a synthesizer that uses really simple algorithm, like enumeration-based algorithm. And so the enumeration will take your search space, enumerate some program from it, and now we've come to actually a really tricky part is, how do we verify that this program is actually correct if we just enumerated it blindly? And the real focus of this talk is actually, how do we verify a program when the input to your verifier is also the semantics of the language in which you're doing verification in? So here we're trying to prove that the program P satisfies the specification when interpreted in the semantics that the user provided to you. And so this talk is just trying to figure out, what do we put in this box here to make this actually work? And so when the specification is just example-based, this is already done by the original work on SemGIS. But what happens when we went to use quantified logical specification? This is work that hadn't been done until my paper. And so let's go ahead and talk about this through a couple of examples. So here's, going back to the original example, the max problem. Let's see how we might try to figure this out. As many of you might know, this program here implements max. So we want to try to verify that this program satisfies the specification, which it will. But how can we prove that? So here, what we can do is actually try to find a closed form solution for this just if then else expression. And if we do that, it equals to this SMT term. We can say the semantics of this is equal to this. That's pretty easy to see and pretty easy to figure out because this term is non-recursive. So it has a very easy way to compute the closed form solution by just iteratively defining, going from the leaves of the grammar and building up the semantics of it into just a closed form solution. And then what we can do is take this semantics for the program and substitute it into the specification for the dummy, so for sort of the placeholder of our program max. And we just substitute this. And now we have an SMT formula that we can just give to an off-the-shelf solver. However, this doesn't always work. It only really works for non-recursive programs like we saw here. But this allows us to plug in just a little bit of what that should be in that box. And the first is can this be encoded in SMT? So is this a non-recursive function program? And if the answer is yes, well, we just encode it using SMT and sort of using the encoding that I hinted at in the example. And if it satisfies that formula, well, great, you're done. You've produced a program that satisfies your specification. If not, you just have to go back and re-enumerate. Now, what if the problem isn't encodable in SMT, such as when you want to synthesize a recursive program? And so if you want to do that, we have to sort of figure out some other encoding. And so for this, let's go back to the second example that we looked at, this imperative program here that we want to try to compute the double of x and sort in y using just increments and decrements in a loop. So here, the semantics of this is fairly standard. You got the while false rule and the while true rule. I don't expect you to read them, but these are just really standard semantics that's sort of just inductively defined, as I said. And then the specification here, let's assume that we're looking for partial correctness. And so this is just saying that the input state and output state represented by the prime variables, that our desired function double takes, if it terminates on the input xy, it does so in the state x prime, y prime, and that the final value of y is equal to twice the input value of x. So that's exactly what sort of one interpretation of what that prose might mean. And so we can take this and start trying to figure out how do we verify that the following program actually implements the specification. And intuitively, this is the correct program, but how do we prove it? Well, what we might actually realize is that the semantics, because they're defined in such an inductive way, that the semantics are all constraint horn clauses, and that the specification, because the semantics only appears in a negative location, that this is, again, a valid query to give to a CHC solver. And the nice thing is that for queries like this, they can be solved using a CHC solver. And so, sort of as I'm hinting at, this only works for some specifications, ones in which the semantic relations appear negatively in your specification. So this sort of corresponds to the class of partial correctness. So we sort of get to fill in just a little bit more of this box and saying if it's a partially correct specification, we can then encode this into CHCs and verify it using a CHC solver. And so just like you did with the SMT case, if it says yes, you're done. If no, you repeat. Now, the last question is, what do we do if it's not encodable into CHC? Well, that means, so that sort of corresponds to like, what do we want to do if we want to try to prove total correctness of a program? So the answer here is that let's go ahead and look back at the same example again, but instead consider a slightly different specification. This is a form of total correctness. It says that for every input state, there needs to be an output state, that the program goes from the input state to the output state, and the final value of y is equal to 2x. So this is just flipping the definition, saying that there has to exist this execution here. So now that we know, now that we sort of look at this, this is not encodable into constraint horn clauses, and so we can't just use the same exact method that we did last time. And sort of the real intuition behind this is that the semantics aren't, exactly defined the same exact semantics as CHCs. Instead, it's exactly the least solution to these rules, or like the least fixed point of this. And if we want to really reason about every possible query or specification from our semantics, we need to really use a logic that supports least fixed points as sort of a first-class citizen of the logic. And so we can actually translate this into a more general fixed point logic, such as MuCLP. And so the while rules sort of just gets simply translated into this least fixed point equation in MuCLP, a logical fragment described in POPL 2023. And so here it just combines the two rules for while, the while false rule and the while true rule, into saying that the semantics of while is defined as the least solution to this definition, along with all the other rules for defining the rest of the elements in your language. And you can do that you can do this translation like grammar point by grammar, grammar element by grammar element to get an entire MuCLP formula for your semantics. And then you just combine that with your query and you can give it to the MuCLP solver, which is great. And so now we finally have the last component that says if it's neither SMT encodable or CHC encodable, it is MuCLP encodable because it's just general enough to support every SIMGUS verification query. And again, if it says yes, you've got a program. If not, you have to re-enumerate. And now we've sort of got a closed loop of our verifier and synthesizer enumeration that sort of can solve or verify any possible SIMGUS problem just using existing logic solvers by doing various like encodings and just translation from one logical fragment to another. So now we have a verifier for solving any possible specification with quantified logical specifications. So one thing when we were implementing this is that we noticed that we don't make full use of the MuCLP fragment of logic. In fact, we only need to use least fixed points, where MuCLP allows arbitrary alternations of greatest and least fixed points in its definitions. And so that got us to ask, is there any meaningful extension of SIMGUS that actually makes a greater use of MuCLP's capabilities? And the answer to that was actually yes. We could modify our definition of semantics to get it closer to MuCLP, and this allowed us to represent not just functional synthesis problems, which the original SIMGUS framework only supported, but also reactive synthesis problems like controller synthesis or Buki games or stuff like that. I'm not going to give an explanation, an in-depth example of here because of time, but the last part I want to talk about is like sort of evaluating this. And so we actually evaluated this on a number of benchmarks that we collected from the SIMGUS GitHub, as well as some new problems for the reactive synthesis encodings. And so they come from 9 different domains, showing how sort of like general this technique is by just using logic. So it includes encodings of SIGUS problems, imperative array manipulating programs, imperative functional integer manipulating programs, Boolean expressions, regular expressions, a DSL for representing scorecards, as well as several reactive synthesis domains like controllers using LTL expression, LTL specifications, strategy for using robots, and also like these reachability Buki games that are very common in reactive synthesis. We sort of evaluated our verifier alone without synthesis by for each synthesis problem having one problem that satisfied one program that satisfied one program that did not satisfy each specification or problem. And then sort of to point out of the 730 verification queries that we tried, our virtual best solver solved 709 out of those, while like each one solved around 525 to 575 of these different encodings, so the SMT encoding, the CHC encoding, and the general MUCLP encoding. And so we also broke it down per benchmark. I don't expect you to really read this whole table, but it's just that it worked pretty well for most of these domains. And you know, generally, if something could be solved as an SMT theory, you should solve it using that rather than CHC, rather than MUCLP, because of how the solvers sort of scale to those kinds of complexities. And then finally, we evaluated this in a synthesis and an enumeration-based algorithm, like we were sort of showing in the presentation. So we incorporated an existing enumeration-based solver for SIMGUS by just replacing its verification routine with our own verifier. And we were able to solve 135 SIMGUS problems with logical specifications, 74 of which could not be solved by any other existing solver for SIMGUS. And I just would like to thank my collaborators and let you ask any questions. Thank you.
Questions? So did you manage to compare against reactive synthesis solvers?
So we did not actually do any synthesis techniques for reactive synthesis, as the underlying SIMGUS solver, like enumerator, doesn't actually work for the extended we had to extend the framework to allow even writing down or encoding these other reactive synthesis solvers, and we just didn't have the ability to change the solver, the enumerator to handle the enriched framework.
But then your evaluation had controllers and games.
Yeah, so this is the verifier, which is able to do these things.
Okay.
What we expect is that if you were to try to update this, we wouldn't scale as well as specialized reactive synthesis solvers. And the key point here is that if you've got things that are kind of weird and weren't, solvable in these like pre-existing solvers, like these specialized domains, that you could actually implement this and get something like a baseline for these other things. And so this is sort of like designed to be used for like lower resource problems. And so at this point, it really only scales to sort of smaller programs. If you get like to 100 lines of code, it doesn't really work.
Okay. And do you have ideas on how to scale to beyond?
Yeah, so the idea is like trying to take sort of like these domain specific, so just as we did with saying this is an SMT-like problem, this is a CHC-like problem, using sort of inspiration from domain specific techniques to try to generalize those and sort of like what's the essence of what's required from the semantics or what's required from the syntax in order to implement these techniques, like sort of invariant generation techniques or like type-directed verification techniques, and try to sort of apply those, like generalize those and say, hey, if it's like this kind of problem, we can apply this more domain-specific technique.
Makes sense. Thank you.
Thank you.
And okay, so let's thank Charlie again.
Okay. Welcome, everyone, to the industry session. We are very fortunate to have several fantastic talks. To kick things off, we're going to figure out what to do about the problem of memory unsafe languages. So I feel like at PLDI, we already know the answer. It's use a memory safe language, duh. But the reality is there's billions of lines of code that aren't going away. And so we have to figure out how to gracefully make this transition and have things work together. And it's an incredibly hard challenge. So Yoel's going to tell us about work going on at Apple to make that happen. Let's welcome our speaker.
Thanks so much. Thanks, Zach, for the great introduction. Hi, my name is Yoel, and I work in Languages and Runtimes at Apple. Our group works on things such as programming language design, compilers, and related technologies and tools. Memory safety in large code bases is not a solved problem. Large programs usually include code written in multiple languages. This means that achieving memory safety for a whole program requires safe interoperability between multiple languages, especially between safe and unsafe languages. In this talk, I'll discuss some of the open problems that we'd love to see more research into from this community. And I'll talk about the work that we've done with Swift, which we think will be generally applicable to other languages. Over the last decades, memory safety bugs have accounted for about 70% of the severe security vulnerabilities across the industry. Even today, attackers against security-sensitive systems are mainly targeting memory safety vulnerabilities. You might be wondering why memory safety is still an issue, and Zach already talked about it. Haven't we solved this problem yet? In theory, yes, there are memory safety languages, such as Java, Rust, and Swift. Using languages like these remove most of the memory safety issues. However, in practice, no, the problem hasn't been solved yet. The problem is that there are billions of lines of C code in C and C++ code in production, and only recently, people have seriously started adopting memory-safe languages in some of those large code bases. For example, the Linux kernel has been written in C as the main language since 1991. And the Rust for Linux project was created in 2020 to add some new code in Rust. However, as of today, the Linux kernel still has 96% of the C code and 0.1% of Rust. In fact, it has more Perl scripts than Rust right now. Large code bases like that cannot be rewritten in a new language overnight. A large number of the maintainers have been writing in C and or C++ for decades. So there can be a learning curve and some resistance to switching to a new language immediately. Even after the maintainers overcome that barrier, because of how the languages are different, switching may require major restructuring, significant testing, and qualification efforts. Please note that it's not specific to a certain language. This is a general challenge in adopting a new language in existing large code bases. Instead of rewriting everything all at once, gradual adoption allows you to start small and build over time. The common approach to gradual adoption in large C and C++ code bases, such as the WebKit browser and the Linux kernel, involves writing new code in a safe language or rewriting some security-critical components in a safe language. However, gradual adoption only works if the safe and unsafe languages can interoperate seamlessly. Here, interoperability means calling a C or C++ from a memory-safe language, calling a memory-safe language from C or C++, or using data structures defined in the other language. In this setting, safe interoperability is crucial. Otherwise, memory safety will be compromised. And we think safe interoperability is a very rich topic for research. Especially, I want to call attention to 4 different problems here. Let me go through each of these in order. Consider a C function like filter image that takes a pointer and the size of an image. And imagine a safe language calls this function. That already sounds a bit unsafe, but there's a way to use this C function correctly. For example, by passing the correct size. But these requirements are not encoded in the type system in C or C++. So the safe language doesn't know how to use it safely. As a result, there's nothing preventing the safe language from using it incorrectly. For example, by passing a size that's too large and causing an out-of-bounds memory access, or by freeing the memory while the C function still holds the pointer for later use. Then there's a problem of reasonably inferring those expectations. That will require pointer analysis to understand all aliases of the pointer and how they are used. However, pointer analysis tools for C and C++ are not yet up to the task due to the difficulty posed by undefined behavior and implicit assumptions inherent in these languages. Even if those expectations can be inferred at the language boundaries, enforcing them within C or C++ itself is challenging. This is because these languages lack abstractions to enforce safety properties, such as bounds of memory, how long this memory is valid, and who owns the memory. While C++ provides some more abstractions than C, they are still not comprehensive enough to guarantee whole program safety. And because unsafe languages like C and C++ don't explicitly express the expectations and requirements, formal reasoning about systems composed of safe and unsafe languages is challenging. It's important to ask and answer questions like, if the end-to-end system still memory safe, and how to ensure memory safety problems must be due to unsafe code. While many of those issues remain unresolved, there has been a lot of ongoing research in this area. And we've also done some work in the context of Swift. I'll talk about how we approach these problems. Swift is a memory safe and cross-platform programming language. It's statically compiled and has a small runtime, so it provides good performance for systems programming. Swift is designed to support incremental adoption in existing C or C++ code bases. Its compilation model allows direct calls between Swift and C or C++. That is, the Swift compiler can export a Swift interface as a C or C++ header, allowing C or C++ code to directly call a Swift function. Similarly, Swift can directly import C or C++ headers so that C or C++ types and declarations are interpreted as if they are written in Swift. For example, this C function is imported into Swift exactly as if it were declared like this in Swift. Swift has historically imported C pointers using unsafe types. In this example, the image pointer is imported as an unsafe mutable pointer. In Swift, these unsafe pointer types are just as unsafe in Swift as they are in C. And this unsafeness is a general problem that arises whenever any unsafe language needs to interoperate with C or C++ pointers. So, Swift has recently introduced a safe pointer abstraction called span. Span is a safe view of contiguous memory owned by others. Span guarantees bounds safety by tracking the bounds information and performing bounds checks at memory accesses. It also guarantees lifetime safety. Swift enforces that spans cannot escape the immediate context or cannot be used beyond the lifetime of the objects they depend on. Ideally, a C pointer should be directly imported as a Swift span. That will make the interoperation boundary safe. But the problem is that C and C++ pointers are missing bounds and lifetime guarantees. To close those gaps, Swift's strategy is to allow programmers to express bounds and lifetime requirements for C and C++ code using annotations. Then Swift understands these annotations and uses them to import C or C++ code as safe Swift alternatives. There are many annotations for C and C++ code that Swift can understand now. But when it comes to pointers that do not own their memory, there are largely two groups of annotations. First, there are bounds annotations that turn the annotated types into dependent refinement types that depend on other values that contain the bounds information. This work is inspired by the academic work on the deputy system that was published in 2007. Additionally, there are some annotations that provide a concise way to express the lifetimes of memory. And these same annotations can also be used to enhance safety in C and C++, which I'll cover later in the talk. Here is an example of annotations that Swift can use to import pointers as Swift spans. The counted by annotation expresses the bounds of the underlying memory. In this example, the counted by image size on the image pointer means the pointer has at least as many elements as image size. No escape annotation is a kind of lifetime annotation. It indicates that the function doesn't keep the pointer after the function ends. This annotation is necessary to preserve the invariant of span that it must not be used after the underlying memory has been deallocated. By adding these annotations, Swift can understand the expectations and requirements for the C function. As a result, the function can be safely treated like a Swift function that takes a span directly. That way, Swift code can directly pass a span type to call the C function without using unsafe types. Behind the scenes, the compiler takes care of correctly extracting the pointer and the size from the span. So there's no possibility for a programmer to make mistakes. And the Swift code must use the C code correctly. However, manually adding all those annotations is a lot of work. So it's important to reasonably infer them automatically. There's a body of research about inferring bounds, but more research is needed to infer other safety properties. And even inferring bounds is not conclusive. While securing the boundary is a good start, we don't want to ignore the fact that as long as C and C++ remain unsafe, bugs there can override the safety guarantees made in the safe language and at the boundary. There have been many mitigation techniques for C and C++, but they haven't been sufficient to stop attackers from exploiting remaining bugs in that same category. Therefore, techniques that eliminate entire classes of bugs are incredibly powerful. They direct attackers to focus on exploiting different categories of bugs that are harder to exploit. Additionally, when investigating exploits and bugs, These techniques enable us to focus on the main classes of bugs that are not protected yet. To achieve this, Apple developed a new extension for C that guarantees bounce safety. This extension uses the same bounce annotations that are used for safe interoperability with Swift. The bounce safety extension is similar to Deputy, again, prior art that uses a dependent type system for bounce safety. However, our noble contribution lies in the combination of dependent types at the interoperation boundaries and the use of white pointers everywhere else. White pointers are automatically carry bounce information, so this approach makes it easy for programmers to grasp the programming model and reduces adoption burden, while still maintaining gradual adaptability thanks to dependent types at the boundaries. Here is a high-level overview of the bounce safety extension. The compiler guides programmers on where it needs more bounce information through diagnostics like this. Then the programmer can add bounce annotations there. And then the compiler inserts bounce checks on memory accesses using that information. This technique eliminates direct bounce safety problems in C code. The bounce safety extension has been adopted in millions of lines of production code at Apple. Based on our adoption experience, its performance impact on the whole operating system was negligible. The extension is open source, and our goal is to standardize the programming model in C. For this, we have recently started engaging with the C Standard Committee. Okay, let me recap. Safe interoperation between safe and unsafe languages is crucial for memory safety in large code bases that are historically written in C and C++. There are still lots of open research problems in this area, and we've only started tackling some of the problems in practice. I've talked about bounce and lifetime annotations to describe requirements in C and C++ code, but there is more work to do to support more language idioms and other safety properties. Reasonably inferring the requirements for C and C++ code is still an open problem, as pointer analysis tools for C and C++ are not up to the task yet. I've talked about enforcing bounce safety for C using the same bounce annotations, but enforcing lifetime safety and other safety properties is much more challenging. Formally reasoning about safety in mixed language settings is still an ongoing research topic. Additionally, designing the interoperability feature so that it's simple to use and fast to adopt is crucial for large-scale adoption. This helps avoid programmer mistakes that can turn into a security problem. Swift approach to directly importing a pointer as a span by using annotations helps with this. But there are still many other language idioms to support. If you found those problems interesting, Swift is a great platform to start. It has a large open source community and builds on Clang and LLVM. We are hiring summer research interns every year. We have a sponsor table over there, so please come talk to us about research collaborations. You can also find us online in LLVM Memory Safety Working Group and Swift forums. Please also check out the safe interoperability documentation in the URL at the bottom. Thanks for listening.
Okay, great. I think we have time for a couple of questions. I saw this hand first. Please introduce yourself.
I'm Sasha from Australian National University. Could you please go back to the slide where there is a compiler inserted bounce check? And yeah, so here I think the check is redundant. Will it be removed by the next optimization, or will it be present?
That's really a good question, thanks. So yes, in this example, the compiler optimization actually is able to remove this bounce check because it considers it's redundant. So for this, we worked with the compiler backend team to implement the LLVM path called constraint elimination that exactly tackles these issues.
Hi, thanks for the great talk. I'm Singhyun Nam from SNU. So in your talk, you mentioned about the way of fixing the memory problem in C++ code by adapting the more memory safe languages like Swift or Rust. But recently in C++, they're aggressively adopting new memory safe types like spans, string views, smart pointers, and stuff like that. And they argue that just like rewriting the code in memory safe languages, they can actually rewrite the code in more memory safe types incrementally. So, and they argue that they can achieve the same goal using this approach without fiddling with other languages other than C++. So, what is your opinion about this approach?
All right, thanks for the great questions. So here I just shown you the C extension, but we also have a safe purpose model for C++, which exactly uses safe span types for instead of raw pointers for memory accesses. But the thing is, span types doesn't have lifetime. The C++ spans don't have lifetime guarantees, whereas Swift or safe languages have lifetime guarantees. Also, string view the same. So, like for C++, it's the same, like similar situation. Although it has more safer abstractions than C, it doesn't guarantee memory safety properties by default.
I think we'll do one more question while we switch laptops.
Yeah, hi, thanks for the nice talk. Ralf Jung, ETH Zurich. Also, thanks for those compiler passes because Rust also greatly benefits from those, I think. So speaking of Rust, one thing I was wondering is Swift and Rust both are talking a lot about C++ interop right now. Have you given any thought to Swift and Rust interop and whether there's anything interesting we could do there? Because they are both languages actually are safe already, just not in exactly the same way, but still that should be useful somehow, right?
Yes, so I'm not here to compare these languages, but I think the same approach can be also applied to Rust. And I know like CrewBit project is trying to do something similar. But I think the key difference, just my own knowledge, is that Swift supports interoperability as a first-class language feature. So Swift compiler directly imports C++ headers, and it understands C codes because Swift embeds a claim. So in that way, I think it's, my own opinion, is more convenient to interoperate with C and C++ with Swift.
Okay, thanks.
All right, let's thank the speaker once again. We have another treat especial. Shenyu's here to tell us about the Tangi language out of Huawei, part of the Harmony OS. I often hear people complain that we don't get enough papers and talks about language design. So if you've ever felt that, you are in for a treat. We've got one here. Please take it away.
Thank you. So this is Xinyu Feng from Huawei Programming Language Lab, also from Nanjing University. So I'll introduce the Tangi language at Huawei. Tangi is a new programming language for mobile application development on Harmony OS, which is a new operating system for Huawei mobile devices. So with this new language, we can have a better vertical integration of the whole hardware and software stack to deliver better programming experience or performance to our developers. Also, the language itself is a general purpose language. It can be applied in other scenarios like microservices. So the language is a modern statically typed and garbage collected language. With ARVM-based backend, it supports native compilation. And it's also a multi-paradigm language. So the name comes from the ancient Chinese sage who is supposed to be the inventor of Chinese characters. So here we have a nice picture of this person, Tangi. Here I'll list some of the key language features of Tangi, including this algebraic data types and pattern matching, unbox value types, green thread, object-oriented programming, type extensions, macros, and effect handlers. I show the availability of these features in other languages. This is not intended to be a thorough comparison or a fair comparison, just to give you some idea how these features are adopted in other industry-level languages. This is a lightweight thread in Tangi. We use this spawn keyword followed by a lambda expression to create a user-level thread. It returns a future type so that you can get the return value of this lambda. So the implementation is stack-based instead of stackless, so that at the programming level, we don't have to worry about this async await modifiers. It also supports dynamic stack expansion. So we have a low latency concurrent compact GC. This is quite important for UI intensive applications where people really don't want to have delays during the operation. So in the implementation, we introduce read barriers for global variables so that we can eliminate some of the synchronization points and reduce the delay of the stop the word period. And on the right-hand side, we have an experiment showing that the delay time for Tangi, it's the blue numbers, which is usually below like 10 milliseconds. Most of the time, it's around 1 millisecond, so which is quite reasonable. I want to point out that the implementation is based on ARVM. It's a moving GC, so it could potentially be a good contribution to the community, because it seems so far we don't see many mature implementation like this. And for performance, we did some experiment using the micro benchmarks from the benchmark scheme website. So, and we did this comparison with Java. It seems that the performance is at the same level with Java. And for some of the test cases, actually, it behaves even better. And also, one of the goals of the design is to have some kind of language extensibility. So we want to use Tangi as a host language so that above this, we can build embedded domain-specific languages. So when we design the language features or the syntax, we try to make them DSL friendly, like operator overloading or micro-programming or some special kind of syntactic sugar. So with some experiments, actually, we can now support these different style of domain-specific languages embedded in Tangi, like HTML or SQL or Prolog-like style programs. Also, we have a preliminary implementation of contract programming so that people can mark, can use annotations of pre and post conditions and invariants, and then do this some runtime testing. As an example of our domain-specific language, we also have an implementation of an agent DSL. We call it Tangi Magic, which is now an open source project online. So in the language, we can have a simple configuration of an agent about the models and the planning strategy. We also have several prompt patterns provided to simplify writing prompts. Also, as a syntax for multi-round conversations with agents, and the framework also automatically maintains the chat history. We also, with operator overloading, we introduce have a declarative style of multi-agent coordination. So next, I will spend some time to introduce the support of effect handlers in Tangi and some of the applications. So many of us are already very familiar with effect handlers. So here in this try block, when we perform an effect, it's like a throwing an exception. So we jump to the handler, and then we get this resumption as a first class value so that it can be stored in variables. It's like a continuation. Then later on, we can use this resume to jump back to the place where we perform the effects. So we know this is a very powerful language feature which can be used to implement all kinds of control abstractions like coroutines. But at the same time, it could be overly expressive. People may abuse this to write unreadable code. So that's why we also introduce a more limited form we call immediate handlers or resumable exceptions. Here, resumptions are implicit. So programmers don't have access to the resumption value. In the handler, they can only either drop the resumptions or do the resume immediately. So the resumption cannot escape the handler block. So even with this limited form, we found it's already very useful because this kind of dynamic scope of handlers, it gives us the ability to implement something like dependency injection. And also it allows more efficient implementation than the general form. So next I'll introduce some of the experiments we do based on these immediate handlers. So in our UI programming, on the left-hand side, we write code to configure the parameters of the UI components. Actually, for each line of the code, the underlying implementation calls the native C++ code. So as you can see from during the execution, so we always go across the boundary between Tangi and C++, go back and forth. This introduces lots of performance overhead. To address this problem, the so-called FFI coalescing tries to intercept all these foreign function calls from the Tangi side and batch them and forward them to the C++ side. So in this way, you only go across the language boundary once. Okay. And then we use this effect handler to collect all these function calls. So the idea is that in our original implementation, we do the foreign function calls directly, but now they are just effects. Then in our handler, we collect all these function references and arguments and put them in this list. And then after all the function calls are collected, we forward them to the C++ side. Okay. So the next application is to use effect handlers to do some kind of reactive state programming in the UI framework. So UI state changes require querying the UI tree to identify and update these dependent properties. So then to do this, we define these state operations as effects. And then so in this try block, we may access the states. And in the handlers, what we do is actually checking the dependency relation. And also we propagate these state updates along these dependency relations so to implement this reactive programming. And the next application is a domain-specific language, which is similar to CSS-style programming for component configuration. So here in the UI code, we can see that for the same kind of components, we usually have the same style configuration here. So it's lots of redundant code. Actually, we try to define this kind of configuration as effects. So we do this configuration in the effect handler. This way, we can have this nested style definition, which is very similar to the familiar CSS programming. So these are the main language features. Next, I want to introduce some of the key challenges and the ongoing work. So the first one is about DSL programming. As I explained that we want to use Tangi as the host language so that we may have embedded DSL, which means we want to support mixed programming of the host language and DSL language. So in this example here, in this DSL program, it may refer to variables and types defined outside in the general purpose language. So the challenge here is to provide a unified language experience between this host language and DSLs. So another issue, which is also well known for people working on meta programming. So the problem is that we want to lift these error messages generated by the compiler for this general purpose host language to the specific domains. So in this example, this is a very simple example. The code on the top is trying to do some addition of vectors. So A and B are supposed to be arrays. But here there's a mistake. So B is an integer. So the expected error message should be the complaint about type mismatch. But if we expand the code, expand the macro, actually we can see that the code below accesses the size fields of B. Also, it uses the indexing operator to access the elements. So we'll get complaints like there's no size field for integer type, or there's no indexing operator for integers, which would look totally confusing to these domain programmers. So the next problem is about cross-language interoperability. I think our previous work explained this issue very nicely. So the interaction between this managed language and C, C++ cause lots of memory safety issues. Actually, in Tangi, this is also one of the major sources of memory safety problems, although Tangi is supposed to be a memory-safe language. So to address this problem, we probably need some tools to support cross-language program analysis. Also, we need to introduce rich types, as also mentioned in our previous talk, to have a nice signature for these foreign functions. But here is another issue, which is the interaction between managed languages, which probably not so thoroughly studied. So here, Tangi need to call libraries of other languages like Java or ArcTS. ArcTS is an extension of TypeScript, which is also an application language for Harmony OS. So here, in this kind of scenario, so both languages have their own garbage collectors. Then the garbage collectors need to cooperate. Then there's this nice PLDI paper actually pointed out that we may have several issues. Actually, these issues also show up in our, in the real programs in our projects. So one of the problems is that the nodes, the objects may follow cycles on both sides of the languages. And then the garbage collectors may not be able to collect all these cycled nodes. So this causes memory leak. The second issue is that although there are no cycles, but if we have a long list of nodes which go across the language boundary, it will take multiple rounds of GC of GC on both sides to finally collect them. So it will slow down the memory collection. So this paper also proposed a nice mechanism called refgraph GC, so which seems to be a nice solution for this problem. Currently, we are trying to have a prototype implementation, but the problem is it still doesn't have a good support of the paper doesn't show the concurrent implementation. It just stops the word implementation. So we want to study how to make this concurrent so that it doesn't cause more delays. Also, it would be interesting to study that in the same process, the Tangi side may want to interact with multiple languages. So it would be important to extend this mechanism to support interaction with multiple GCs. The third issue is for ABI stability. So high-level languages promise that we have a better abstraction. People usually don't need to worry about this low-level implementation detail. But if we care about separate compilation, or if we work on this cross-language interpretation, so we have to understand this binary format, including this calling convention, memory layout of data types, or even name mangling. So, and these are the several scenarios that we need to care about this. So the application need to do this dynamic linking with the library, which is on the operating system side. So if the library evolves and the binary format changes, so the linking could fail. Or maybe the library is the same, but the compiler is upgraded, and we recompile the library, which may also break the compatibility of the binary format, so the linking may still fail. And then the third scenario is about the cross-language operation. So, so the problem here is that we have to be careful. If we want to give some kind of promise of this ABI stability, we need to be careful with the trade-off between flexibility versus performance. One way is that we hardwire all these ABI formats in our specification so that the compiler can still do the optimization. But then it would be too rigid for the compiler to make any changes. Or we can introduce some runtime resolution. So this gives us flexibility, but this also affects performance. Another issue is that we have to handle lots of these tedious low-level details. It will be important to have some systematic approach to describe or specify this ABI. So it was nice to see some of this work along this line. And also, it's important to have tools to do checking or testing of ABI conformance. So these are some of the problems that we feel maybe deserve more attention from our research community. And also there are other challenges and ongoing work, like we are considering introducing ownership types for better memory and resource management. And also we are building tools for this cross-language source-to-source translation so that people can import their legacy code to the new language. Also, we need some effective ways to do this compiler or runtime, including GC testing. And we want to minimize the compilation time with some incremental or parallel compilation approach. So there are also other problems which are on the list. So anyways, we have on the website, we have an online playground. People can try if you are interested. So feel free to try and contribute. This is the end of my talk. Thank you.
Okay, we've got time for a few questions. Any hands up? Let me see, and we'll bring the mic over to you. Oh, there's one.
Hi, this is Song from NYU. I'm really curious about Tangi being built with Harmony OS in mind. Are there any different technical considerations such as scheduling, because you're working now in a microkernel architecture rather than a monolithic kernel?
Yeah, actually, indeed, scheduling is actually one of the most feature that we want to have a vertical integration, so-called vertical integration. So one of the issues that we have is that applications may want to create too many threads. They may be selfish, and then the uniform system level scheduling thread management mechanism can have effective control of this. So the language want to have a good coordination between with the system level scheduling approach.
Hi, Thomas Gilray at Washington State. Really enjoyed your talk. You mentioned that you're able to optimize these second-class resumptions for effect handlers. And I'm wondering if that makes the stack kind of like a zipper structure, or if you're using inlining, if you can speak to what you're able to do to optimize these, given that you don't have first-class control.
Well, I'm not an expert here, but I guess what I heard was that because this resumption doesn't even escape the handler, I think we avoid this stack copy or something. But we can discuss the detail offline. Yeah.
Hi, I'm Christine Riscala from the University of Melbourne. Yeah, thanks for your talk. I was curious if you have any plans, like for verification or that sort of thing?
Verification. Yeah, so actually, we currently, we are trying to export high-level intermediate language, so which may serve as an infrastructure for program analysis. And also, yeah, so we also have some kind of collaboration with universities to have like formalization of the semantics, also maybe some of the algorithms.
Hi, John McCall, Apple. You said that you have growable stacks, but you also have C and C++ direct interoperability. How do you manage the stack problem, or did you also change the stack model in C?
We don't feel it's needed. We are doing this. Oh, so okay. I mean, in that case, you can't grow the stack. I think.
Oh, okay.
Yeah. Okay.
Let's thank the speaker again, and we'll switch over to Sunho next.
Test, test. Do you hear that?
Yeah.
Yeah. Test, test. Test, test. 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 Test, test. Test.
슬슬 앉으라고. 네? 지금 몇 시예요? 지금 7시 넘었어요. 7시 2분. So hello everyone. Hello everyone. So the banquet will start within a minute, so please have a seat, please.
You can use your utensils.
This one? I don't know. So here, just,
He's very active on that. Yeah. Is this Skills mic?
Yeah.
Jiung, right?
Yeah, Jiang. Yeah. Yeah, I think. Yeah, just come off the mic. I give this one to Gil. Yeah, thank you.
Oh, one important.
Yeah.
Don't hand your mic to other people. We have additional mics.
I see. 여기 앉으셔야 되겠는데. 여기 한 자는 안 거의 다 온 것 같아요. 거의 꽉 차는 것 같아요. 거의 꽉 찬 것 같아요.
banquet and all the ceremony. And this is a sign for the step to start serving. So if I finish this comment, you will get food. Okay. So it seems almost full. So actually, filling this place is quite hard problem, because if you have too many, then we may have some left. And then also if we have too few, then also we cannot serve more. So expecting how many people will come is very hard, but looks like we made a very good estimate. And because your dinner is quite expensive, each person, it costs quite a lot. Anyway, thanks a lot. And so, are you happy with the food and place here? Yeah. Okay, thank you. So, Jiyoung, where is Jiyoung? So Jiyoung made a lot of effort to somehow make this food, nice food and enough food. And so please, let's thank Jiyoung. Yeah, thank you. Yeah. Okay. So it looks good. So we can start ceremony immediately, right? So okay. So thanks all, and then the ceremony for awards will start. And I will pass this mic to who? No one? Okay, I'm in charge of this. Okay, I didn't expect. Okay, then I have no idea what. Okay, computer is here. So, but this screen doesn't appear. Can you switch the screen? So anyway, this sign consists of Korean letters, has gone, but the design. Yeah. Also, the idea was mine, but the design we hired the designer to do this, and these colors are all Korean color. So this color is traditional Korean color for roof, and these are colors of our Korean traditional cloth. So I think it's quite pretty and a good choice of color. So anyway, I wanted to mention that, and yeah, thank you. Okay. Yeah. So, yeah. Okay. Thank you. Okay, and we can we always grateful to the fantastic sponsors. Thank you all sponsors, especially Apple, Amazon Web Service, and Huawei. I think, is there anyone from Apple here? Okay, thank you. And also Amazon Web Service. Okay, thank you. And Huawei, please raise hands. Okay, thank you very much. Yeah. Okay. And okay, yeah. So yeah, this is agenda. It's hard to see. PLDI distinguished paper awards first. And Jack, I think you can come. And so the next slides, I think, I think I'll pass the mic to you. Okay, thank you.
Okay, everybody. So we've got 6 papers that were selected for Distinguished Paper Awards this year. The program was really strong, so we have a few more than last year. To kick things off, I guess the slide is up. So would the authors of Verifying General Purpose RCU for Reclamation and Relaxed Memory Separation Logic please come up? advance the photo. Thank you. Congratulations. Okay, drum roll. Next up, we have this audit paper. See the spelling? It's like a joke because it sounds like audit. On database isolation testing. So if Lasse and Andreas could come to the front. Congratulations.
Thank you.
Yeah. People really love this one. Oh, good. We have to get inside the box.
This box?
Yeah.
Do I hold this?
I think we just look at Nicole and smile, but not too goofy.
Okay.
Oh, we get the background. Thank you very much. Congratulations. Next up, if the tree authors of Tree Borrows would come up. This was another paper that people were very excited about. Congrats, everybody. Okay, and Derek, just come back. Destabilizing iris, we were also fantastically excited about. And we additionally had two papers people were very excited about on type systems. One on practical type inference with levels. And last but certainly not least, a fresh look at static overloading using principal type inference under a prefix. Yeah, there we go. So these papers were selected by nomination from the PC and then reviewing the reviews and discussion with Gil. It was actually nice. The last two papers both involved Coca, which was really interesting as a research platform. Lots of stuff involving proof assistance and also people are very excited about hardware. So I think those are sort of reflecting some of the themes that had the most engagement and enthusiastic reviews from the process. I think with that, there's one other thing. Which is we wanted to highlight some of the reviewers who did, we had fantastic PC this year, but a handful of people were really stood out by having more than half of their reviews get flagged as positive by their peers. So this is, writing a good review is really hard. An over 50% rate where multiple of your peers select this as a particularly strong review really stands out. So let's congratulate all these people for their Fantastic reviewing. And if you're in the room, please stand up. I saw Chris somewhere, and maybe some others. Yeah, Chris, I see you. Yeah, okay. So if you see any of these people, please give them an extra hearty thanks. We really appreciate it. It's a lot of hard work, and these people are what help drive the community forward. Okay, I think now we can hand it back to Kieran and Ning Ning. Yeah.
Congrats again. Thank you. Where are the certificates? They didn't give us.
I don't know.
Oh, I don't know.
You can ask Naringa.
Okay. Where's Gail? Thinking of both of us. Where's Gail? Okay. Gail. 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 We don't have certificates.
Sorry?
We don't have certificates for the award.
You don't have certificate?
No.
Why?
Nobody gave it to us.
Oh, sorry. Chuck, what happens? No certificate? Oh. Usually Naringa prints them and they bring to Korea.
Okay.
I think she made a mistake.
Okay.
So we can reuse the certificate and
Yeah, we can still announce it.
We can, yeah,
first. Yeah.
And then, but because we got so maybe she got confused. Anyway,
give them a very firm handshake.
Yeah. And then
We will
we
do
will
that.
send. I think Naringa will send them to you anyway.
Okay, okay.
But this is a mistake. Maybe.
I see.
You say something about it, or I say. I think. Yeah, I don't know, but this is certificate is missing somehow. That's a mistake.
Is that bad? I mean, we have the R's. If they can. I don't know.
It's a Naringa's mistake.
Okay. Hello, everyone. We are very pleased to present the PLDI'25 Artifact Awards. And the first paper who received this award is Verified Foundations for Differential Privacy. Are the authors here? Congratulations, but we are missing the certificates. I'll give them to later.
Okay, cool.
Yeah, okay,
Great.
cool.
Thanks.
Congratulations.
Thank you.
The second distinguished artifact award is presented to a hybrid approach to semi-automated Rust verification. Congrats.
Congratulations. Thank you.
Do we have any? It will be mailed to you later. Yeah, thank you. All right, thank you. Next will be SRC Awards.
Hi, I'm Alexa Van Hatten from Wellesley College.
I'm Rachat, MIT and Jane Street.
And we're excited to present the winners of this year's student research competition after the poster session and finalist presentations. If you were a finalist, please come up near the stage because all finalists will be awarded. So start making your way up to the stage now if you presented this afternoon. So starting with the winners in the undergraduate category, in third place with the Bronze Award, we have Andrew Fox from University of Colorado Boulder. For developing a framework for extensible static analysis. Are you doing the photo? Yep. Okay. The Silver Award, we have Ludmila Paskanova from Moscow State University for Asta Kata. And finally, for our gold, we have Jam Kabir Ali Khan from MPI. And for capabilities as first-class modules with separable compilation. Okay.
All right, moving on to the grad category. Our bronze finalist is Prashant Praladhan from the University of Colorado Boulder. Prashant is actually remote, so if he has colleagues from UC Boulder,
From Boulder in the front want to take this. Come find
represent
us
Prashant perhaps, maybe not.
Great.
All right, moving on. Our silver finalist is Jay Lee from Seoul National University. Jay? And our gold finalist is Charles Averill from the University of Texas, Dallas. Charles. All right, and we'll pass it off to whoever is going to announce the most influential paper of PLDI'15. Andrew.
Okay, we have some awards that come from SIGPLAN. So I'm Andrew Myers, the SIGPLAN Executive Committee Chair, but I'm going to be speaking on behalf of the SIGPLAN Awards co-chairs, Alexandra Silva and Nikki Vazu, who could not make it here today. Okay, so the SIGPLAN Most Influential Paper of PLDI 2015. So this is presented annually to the authors of a paper presented at the PLDI held 10 years prior to the award year, and it includes a prize of $1,000 to be split among the authors of the winning paper. So the papers are judged by their influence over the past decade. So the 2025 committee included the 2015 general chair and program committee chair, and last year's general chair and program committee chair, and the awards co-chairs, and Anders Moeller, the vice chair, stood in for me because of conflicts of interest. So the winner is a simpler, safer programming and execution model for intermittent systems by Brandon, Lucia, and Benjamin Ransford. I don't. We have someone. Great. And so I will read the citation here. Energy harvesting enables novel devices and applications without batteries, but intermittent operation under energy harvesting, come on up, poses new challenges to memory consistency that threaten to leave applications in failed states not reachable in continuous execution. This work provides analytical models that aid in reasoning about intermittence and develops DINO, Death is Not an Option, a programming and execution model that simplifies programming for intermittent systems and ensures volatile and non-volatile data consistency despite near constant interruptions. DINO is the first system to address these consistency problems in the context of intermittent execution and dramatically simplifies programming, reducing the set of possible failure-related control transfers. So I have...
We said it Dino, by the way.
Oh, Dino. Sorry, Dino. I'm going to mispronounce a lot of things today, I can tell. So anyway, congratulations.
Thank you.
And here is this. Do you want to say something?
Yeah.
Sure.
Yeah, thank you. This is really a great honor to get an award like this. When we were doing this project, the main reason for getting started was TI made a new processor and it had non-volatile memory, and we thought that was kind of cool. What can we do with that? So we sort of doinked around and found some cool stuff we could do with it. And it turned into a long series of projects that have gone on for really about 10 years, where a lot of my students and now lots of others in the community have been looking at intermittent computing. So it's a real honor to receive this award in recognizing kind of this as a jumping off point for a lot of things that have happened since then. So thank you.
Congratulations. I guess we should get a photo.
Yeah, we should get a photo.
All right.
Cool. Thanks again.
Okay, next up we have the John C. Reynolds Doctoral.
Just go back. I
Yeah.
want to make some
Yeah, absolutely.
Okay. Yeah, thank you. Just sorry for interrupt. I just want to say something. So currently we have 42 meals kind of we couldn't fill, so we want to distribute. So what I discussed was that for each table maybe we can have extra steak, and then also if you want more of your menu, you can just ask. Then they will serve you. So I think students last time, a few days ago, they said the quantity and quality is good, but quantity was not good. So if you want to eat more, so we have a 42 extra meals, so you can freely ask them that they will add other things. So is that good, or maybe any other good idea, like just based on the request, or just extra steak on the table? That's good. Okay, we will proceed. I'm sorry for interruption. Okay, thank you.
Okay. I'm glad somebody's getting to eat. So next we'll talk about the John C. Reynolds Doctoral Dissertation Award. So this is presented annually to the author of an outstanding doctoral dissertation in the area of programming languages. It includes a prize of $1,000. The awardee can choose to receive the award at ICFP, Splash, Pobble, or PLDI. And the selection committee may give multiple awards, which we have done this year. There are going to be 2 awardees. So the Reynolds Dissertation Award recognizes the contributions to computer science by John Reynolds. It is a renaming of the SIGPLAN Outstanding Doctoral Dissertation Award to encourage the clarity and rigor that Reynolds embodied, and at the same time provides a reminder of Reynolds' legacy and the difference a person can make in the field of programming language research. So the committee consisted of Nikki Vazu, Anders Moeller, again because of conflicts, and representatives from the 4 major conferences. Okay, so the awardees are Harrison Goldstein for his work Property-Based Testing for the People, and Rachit Nigam for Modular Abstractions for Efficient Hardware Design. So let me start. I will read out Harry's citation first. He's actually not going to be able to pick up it today because he's not here, but nevertheless, we'll read this out. So Harry Goldstein's dissertation, Property-Based Testing for the People, makes groundbreaking contributions to software reliability by advancing the theory and practice of property-based testing, PBT. His work introduces novel mathematical foundations, free and reflective generators that automate the construction of high-quality test case generators, dramatically improving usability and effectiveness. Through empirical studies with industrial users, Harry identified key challenges in PBT adoption and addressed them with Tangi, an interactive framework that enhances testing visibility and control. His research, bridging programming languages, software engineering, and human-computer interaction, lays the foundation for a new generation of practical, powerful PBT tools with substantial impact across both academia and industry. Okay, next, Rachit, you can come up. So Rachit Nigam's dissertation lays the semantic and practical foundations for a new generation of hardware description languages, applying deep ideas from programming languages to an area long neglected by the community. As the industry shifts toward specialized hardware with smaller agile teams, the limitations of legacy languages like Verilog have become increasingly acute. Nigam's work offers a groundbreaking rethinking of hardware design, particularly through his novel treatment of timing via substructural type systems, enabling predictable and composable hardware semantics. His timeline types innovation in the filament system, which enforces timing correctness compositionally, is already influencing industry practice. Beautifully written, technically deep, and with growing impact beyond academia, this dissertation exemplifies the best of programming languages research and will serve as a guide for future work at the intersection of PL and hardware design. And this work also, by the way, received an honorable mention for the SIGARC TCCA Dissertation Award at ISCA. So congratulations.
Sorry for another interruption. So it seems that no one kind of requested a soft drink. So I have to let you know that we have also soft drinks and sparkling water. So you can freely request those. I forgot to mention this. Okay, we have 100 left, so you can freely order. Thank you.
All right. I should have brought my glass of wine up here. So the next award will be the Programming Languages Software Award. So this award is given by ACM SIGPlan to an institution or individuals to recognize the development of a software system that has a significant impact on programming language research, implementations, and tools. The impact may be reflected in the widespread adoption of the system or its underlying concepts by the wider programming language community, either in research projects in the open source community or commercially. The award includes a prize of $2,500. So the committee consisted of both awards co-chairs, myself, and representatives from the 4 main conferences. Okay, so the winner is the Lean Theorem Prover. Gabriel Ebne, Sunho Kong, Leo Demura, and Sebastian Ulrich. And all of whom, any of whom who are present are welcome to come up. So the Lean Theorem Prover is a remarkable software artifact grounded on strong theoretical and engineering foundations. Lean has had and continues to have a broad impact on industrial practice and scientific research. In particular, the Lean project has already had a significant impact on mathematics, hardware and software verification, and AI. It has gained substantial traction in the mathematics community with a user-developed library MathLib that has more than 1.8 million lines of code. The verification of foundational results at the request of Fields medalist Peter Schulze and the verification of the polynomial Freiman-Ruja conjecture led by Fields medalist Terence Tao have earned the system widespread recognition. It is clear that formal methods based on Lean will play a central role in mathematics in the years to come. Lean is also used in important verification projects in industry, including the verification of the Cedar access control language at AWS, the verification of the SampCert sampler for differential privacy at AWS, and blockchain verification projects at companies like Starkware and Nethermind. Finally, with the success of projects like DeepMind's AlphaProof and the adoption of Lean by startup companies like Harmonic, Lean has become the de facto choice for AI-based systems of mathematical reasoning. Okay, so the final SIGPLAN award that we will be giving out tonight is the Robin Milner Young Researcher Award. So this award is given by SIGPLAN to recognize outstanding contributions by young investigators in the area of programming languages. Individuals are eligible if their computer-related professional career started no earlier than 20 years prior to the nominations deadline. The award includes a prize of $2,500. And the committee included various members of the executive committee dealing with various conflicts of interest and representatives of the major conferences as well. So this year's winner is Ishil Dillig. Ishil Dillig is recognized for her profound and far-reaching contributions to program analysis, verification, and synthesis. Her groundbreaking research has advanced the theory and practice of formal methods, with applications ranging from security vulnerability detection to code migration, relational reasoning, and zero-knowledge cryptography. Her seminal results in abductive inference, neurosymbolic programming, and solver-based reasoning have opened new directions in programming languages and verification research. Dillig's work is distinguished by extraordinary technical depth, breadth, and originality. She has repeatedly anticipated emerging trends, notably pioneering the integration of machine learning with formal methods, including influential contributions to reinforcement learning for program verification and synthesis, and the use of large language models in specification-guided code generation. Across all of these areas, her research combines sophisticated theoretical insight with a commitment to practical impact. In addition to her technical achievements, Dillig has demonstrated outstanding leadership through mentorship, community service, and building a strong research group. Her influence is evident both in her prolific scholarship and in the success of her students and collaborators. Okay, and I think that wraps it up for the awards. Now you can just enjoy your food. Yeah, that's all.
Yeah, we want to say thank you for the committee. We're super happy for the recognition. And I talked this morning, I think Sebastian wants to say something.
Oh, I have no idea what to say, except this has been an absolute journey with a lot of inspirational, super intelligent people on the way. Yeah, so including these on this stage, including many others.
Yeah, it's my great honor to receive the award, and I always think I'm extremely lucky to be in the right place with the right people at the right time. So, and also I believe this award goes to the actual Lean community and all the people who love Lean and using Lean. So, thanks for that. Yeah.
Oh yeah, it's an absolute honor to receive this award. Like I still remember like the first day I joined Lean. Back then it was really small, and like just the massive increase in like usage is amazing. I can really only like thank the community for picking it up and like getting us so successful. Well, thank you.
Great, thank you very much. Okay, and we're going to get Ilshul to come up here and say something.
Thank you. It's been an honor to be a part of this community, and I'm really honored to receive this award. And I just want to say that this award goes as much to all my students and collaborators as it does to me. Unfortunately, this year, many of my students were not able to make it, but you know, it's been a real privilege and honor to work with all of my students, and yeah, this award is really as much theirs as it is mine.
Okay. Yep, thanks everyone.
Okay, thank you everyone, and enjoy your meal. Thank you.